Robertine, sorry.
Yes.
Ready to go? Very good. Okay.
Let me share my screen. Okay, everyone can see?
Yes,
Yes.
I can see.
Perfect. Let me move this. It's fine there. So, today we have a long lesson. That's actually 2 lessons in one. We have the testing and the full DApp stablecoin example. So I'm going to make my best effort to make it on time. And so I will try to not fiddle around too much with code. I'm going to change some stuff just to like showcase when the test break and work as expected, etc. But mostly I will go over the types, I will go over the function, explain how it works. So I think the testing lesson will be the shortest one, but let me know if anything doesn't make sense. Raise your hand or unmute yourself and talk. I don't mind. So we're going to start with testing. To test smart contracts, we're going to use, you can see me switching desktops, right?
Yes.
Perfect.
Now you have a browser open.
Yes, perfect. Thank you so much. So we're going to use the Bluetooth Simple Model Library. And if you use Atlas, like Lars did, it has a wrapper to integrate with this library. So if you understand this, you should be able to use it through Atlas. And Atlas has a couple of things extra on top of it, so that's really nice. But we're going to keep it a bit low level. So this is the Bluetooth Simple Model Library. And you can, if you go to the very bottom, you can just run and debug to get like a nice interface, but we're going to skip that. And we're going to go straight to docs. And source summary. And here you have all the documentation you will ever need to use this, basically. You have the installation instruction, the quick start, using with Tasty, that we are going to use it with Tasty, how to create transactions, etc. We're not going to go over the actual documentation, except maybe bits and pieces. But this is where you have to go if you want to like learn a bit more about how it works in detail. For us, however, we're going to start with the simplest example how to use the library. And we're not going to test, in the first example, we're not going to test a smart contract. We're just going to use it to make transactions. So we, as always, start with the default main to convert the tree into an actually executable an IO action. This comes from the Tasty framework, so it's not part of the Bluetooth Simple model. As well, we have this test group that translate, like the joins, takes a list of test trees and makes a single one to pass to the default main. And a simple explanation of the test group intention. In this case, it's a simple test to check transactions, and then a list of all the tests we want to perform in this test group. In this case, we have one to test if we can spend, like if user 1 can just send some money to user 2. And what happens if user wants a user tries to make a transaction that contains more that the user actually has in their wallet. So that shouldn't work. So these are the 2 tests we're going to perform. And To that, we have to first explain what is this actually, this good and bad thing. We define these two functions here. And the good function, we provide these initialization values of the actual, how the blockchain starts. Actually, if we hover over simple span, we say that we see that the type is of type run Boolean. And what is this run type? Well, if we go to the Bluetooth Simple Model library and search for run, we see that run is just a new type wrapper around the state monad. So it's just a state monad that tracks the state of this mock type. And if we scroll a bit up, we see that this mock type is a mock blockchain, basically. It has all these properties that we care about the blockchain. So every time we run a step in the run wrapper, the state monad, we perform changes to this mock state. This mock blockchain has a map of users, addresses, UTXOs, datums. It tracks, this is important for us, tracks things that fail. So this is basically the state of the blockchain that is going to that we're going to keep track of while performing the tests. So, but to initialize that, we use this test no errors function that takes a mock config, a string, and this run value, and returns a test string. So this is going to, as you can see, we're providing just two of all the values that we want. But so we're just partially applying the test no errors function, and we provide the config, that's default Babbage. We have all these default configs that I think are on the same default. No, let me see. So we have all these default configs, default Alonso, default Babbage, so all configs that we can use, or you can just make a custom configuration for your use case. In our case, default config is just fine. And we provide the initial value, the amount of the initial value that we're going to have in that blockchain. These 10 million ADA are going to be sitting in an admin account, an account that is under our control. All accounts are under our control, but this admin account is like an all-powerful account that holds the first UTXO created in the blockchain. It holds all the money. So every time we want some user to have some ADA or some other token, we have to send it using this admin account. So once we have this partially applied test no errors, we use it to check all the transactions that has to all the tests that has to return without any failures. So that's why we check here in the test no errors, because the blockchain tracks all the as we saw before, we tracks all the failures in the transactions. If there's any failures, we can check at the end of all the transactions that we make if there was any failure. So that's what we're checking with the good. We're just checking, we are providing some tests, and it has to everything is good if nothing fails. But sometimes we want to make sure that something will fail. Like if the user has less funds that he wants to transfer, it should fail. That's a good thing that it fails. So for that, we take this we take this good function and we apply the must fail function that flips the script around. So now everything is good if we have a failure. That's the two ways of checks of making that's the two ways we have to make the checks. Is everything is good or if something fails. So now the interesting part, all this is basically boilerplate, more or less, except for the list. So the interesting part is actually in the actual test, the simple spend and the not enough funds. So let's go to first the helper functions. Why not? We have just a single one in this case. We need users to perform transactions. So we need to create them and give them money. And this setup users is the function we use to do just that. We have this new user function that takes a value and returns, performs an update in the state of the blockchain and returns the pub key hash with whatever update, whatever any update we make to that pub key hash. In this case, the new user just sends money to the user, creates the user and sends money. And we send money from our admin account. So we send to each user, we send 1,000 Lovelaces to a user, and we replicate this 3 times. So we have 3 users with 1,000 each.
Martin, we have a question. Tony, say, how does the composition in the definition of bad works?
Yes. So, as you can see, the good function needs a string and needs the run state monad. We're going to call it just run from now on. We need the run to actually perform the test tree. But when we apply, we want to use. I'm guessing the issue is with this message here. So we want to apply this message. There is this string right here, as the first value, because good takes first the string and then the action to perform. So I took the first, I explicitly set the message value, I named the message value and pass it as the first. And then once we have this, let's see. Once we have this function, we just need to pass the run function. So actually, for example, if we do something like this, in this case, the must fail, the only thing it does is to change, like to flip the script, right? So now everything is good, is bad, etc. But we are passing 2 parameters here to that function. So we have to take into account that, for example, we can do message in test, and here we can do good message and test. This is how you can write explicitly what's going on. But because my final test but because test is the final parameter on the right and the final parameter, the last parameter on the left, I can just reduce this and compose it with the other, with the good function. That makes sense? So this will be like the explicit version of the function.
Yes, Tony say.
Okay, so we have the setup users function, as we said, and now we have to actually test, create the transactions to test. So we have the simple spend transaction and below the other one. So, but we're going to start with the simple spend. So we know that we have to return a run something, and this run something is a Boolean that returns if everything is okay or not. So we start by setting up our users. We make the admin user to send. Oh, we have another question. Yes, thank you. Okay, perfect. You're welcome, Tony. So this setup users creates a list of pubkey hashes. Let's see, a list of pubkey hashes that we can pattern match to make it a bit more easy to use. So now we have our 3 users with 1,000 loveless each. And then we use the send value function that takes a pubkey hash of the sender, the value that the sender wants to send, and the pubkey hash of the person that receives the value, and returns the action, the state action that performs that change in the blockchain. So we're going to send user 1 sends 100 lovelesses to user 2. And then user 2 sends 100 lovelesses to user 3. At the end of these 2 transactions, we check that all transactions were accepted by the blockchain without any errors. And we check all the values that the users have currently. Remember that in each step, we can update the state of the blockchain. So after checking that these no error functions returns a Boolean, say that if there was any error at some point or not. But also, besides that, if there is any error, we also want to make sure that the values we expect each user has are the actual values that each user has in their wallet. For that, we have this value add function that takes anything that is, it takes a type that is an instance of has address, so any type that has an address, and returns all the value sitting at that address. So we map this value add to each user. So we have the values, a list of all the 3 values of our users. And then we're going to return, remember, we want to return a Boolean to check that if it's true, if everything is right, false, if it's not. So we are going to say, okay, we're going to return true if there's no errors in any transaction, and the values we actually have are the same 1,000 each. So because user 1 sends to user 2 100, user 1 100, but sends 100 to user 3, it stays the same, and user 3 is the only one that gained lovelesses with 1,100. So if these 2 properties hold, that means everything is okay. That's our first test. And the second test is pretty easy. If we set up the users, we give them names to make it easy, and then we try to send 10,000 loveless from user 1 to user 2. It doesn't really matter which users are. None of them have 10,000 Lovelaces. So in that case, we have to check that the transactions we had errors while sending previous transactions. This we sent on actually we sent a couple of transactions because we set up the users. We have a transaction there, and then we have another transaction to send the 10,000 Lovelaces. So if neither of these transactions if neither of those two transactions return fails, the no errors returns true. So in this case, it should return false. So we should have an error in the second transaction, the send value. And because this already the type that we want, there's no need to like run it and it's okay. We already saw that actually this I should have updated this loop here. So this is our second test. In this case, we want an error. We want this second transaction to have an error. So now that we have our tests written, we can run them. We're in the testing folder, and if we do cabal test, and I named the test the same as the name of the file, so Bluetooth simple model. And if we run this, by the way, the Docker images already have all the binaries precompiled finally. So you just have to wait whatever I just wait to compile everything. And that's it. So we have the simple spend that everything is okay because, let's see, everything is okay because it was good. There was no error in a whole set of transactions. And the not enough founds is also okay because we had errors and shouldn't, like whatever happens shouldn't have happened. So that's good because we expected that.
Can I ask a question quickly?
Yes.
Somehow it seems you do this error checking twice. I mean, first you use these functions that come from Bluetooth simple model, this must fail and test no errors, right? That's from Bluetooth simple model itself, isn't it?
Yes.
In your good
Yes.
and bad. But then you also explicitly in your tests you check for errors and then return that as the return value in this run monad. Is both necessary?
You mean this one? And
yes, I mean, I thought, I mean, what exactly does test no errors do?
Test no errors checks. I mean, we have this map of failures.
Right.
It checks that basically that map is empty.
Yes, but right.
Yes.
So why do you in your first test, for example, have to also check this errors and return the Boolean whether there are errors or not? I mean, isn't that supposed to be done by this test no errors or
This one?
function? No, you check there in line 46.
Line 46, yes. This is the check. This is the no errors check.
Yeah, but I thought it's done by the test no error function. Didn't you?
Oh,
I mean,
this one.
yes, I mean, I guess I asked what, I mean, this test no error function checks this map. But what, I mean, where does the return value of the run monad computation, the true or false, come in? I mean, does anything check whether that's true or false?
Yes, because I'm returning.
No, I mean, does tasty or something check the return value? I mean, if you just return false, for example, would it fail? Would the test fail?
The simple spend.
Yeah, if you just like comment out those two lines and just say false. What would happen then?
Wait, let's change this to no, this is good, this is bad.
No, yeah,
Yeah,
leave it as it.
that previously. Let's see. Yeah, I see. I understand what you mean. Right. So
Right.
we are
So
not
the value there doesn't do anything.
right.
The return value.
This
So in
return.
particular, this test doesn't really check that. I mean, if the amounts are wrong, then the Boolean would be false, but the test would still pass.
If the amounts are wrong,
I mean,
right, but
I
we
mean
have
now,
errors.
no, but I mean, I mean, if you now undo this change and put your check in there again. See, I
Yeah.
mean, if the amounts were wrong, if B, for example, had 1,000, I mean, if you just change the amounts, if you change the 900 to 950, for example,
Right.
then it will still pass.
Let's see. Yeah, I see what you mean.
Or it
It's
doesn't.
user
That's
one.
interesting. Oh, okay.
No, that's
but
good. That's okay. So it is the other one that failed.
okay.
Uh,
Yeah. Okay, so that means the return value doesn't do anything for the test.
right. Yes, you're right.
So
'Cause yes.
maybe there's something like an assert, or I don't know to the simple
Yes.
model that well, but maybe there's something where you can explicitly trigger an error if some assertion fails.
Yes, we use an assert further along, but now I'm doubting if
I
that's
mean, sorry for derailing you. I was just
no, that's perfect. This assert comes from quick check, not from as the class.
I mean, where they have this check no error, and I mean, somehow maybe you can like by hand create a custom error.
Yeah. Yes, we have. We can do that. Let's see, doc source here. No. Docs source. If we have yeah, I did at some point create my own error. Let's see.
So I think that, yeah,
These no errors. Well, let's see where it's defined.
yeah, exactly. Maybe that's a good idea. There's something with, I don't know. I mean,
yes, yeah, there is something. Let's go to.
I mean, suppose if there wasn't, you could also do it by hand too. I mean, because the fields of the state monad are accessible, so you could by hand include an error there, I suppose. But I mean, there should be
check errors, testing helpers.
must fit. I mean, that's something else.
No.
Or there was this. Well, there's this
Log error. So weekend log error.
right. Yeah, just try that exactly. If it fails now. I mean, what you actually want is if the values are not what you expect, then you would log this error, right?
Yes, so in that case, I have to like this.
No, hang on.
No, I think
No,
it's
no. I mean, you
after the
want
evaluation. Yeah.
basically you want. I mean, after line 46,
Yep.
You after line 46, you want to say when vals don't equal the list you expect.
Right. Yes, you're right. Oh, what's going on? Yeah. Sorry.
So probably, I mean,
I did.
I think that right, not equals, I think, or unless, I mean,
Unless I think unless
then you can leave the equal. And now you should still, and the no errors you can remove. You don't need that because that's checked anyway, I think. And you must, the last line, 49, you can remove. And you should change the type of simple spent to run unit.
Yeah.
And I think there's
pure. I think you need the pure.
Can you just no, you just need a dollar at the end of the line.
In the end, and the
No pure. No pure. Just a dollar at the end of line 47 or beginning there.
Right.
yeah.
Let's
you return pure. Yeah, sorry. Unit.
No problem. Now it should still fail because the 9 or the when you still need to right. Now you get the error because of the 950, and if you change it to 900, then it should pass, hopefully.
Yeah.
Okay.
So
right. So the method of checking something is not returning false. It's to like log an error and then use this no error function.
Okay. So yes, and I think now that
that means you also in the second one you can also change that line 51 to run unit, and you can remove line 56 as well, I think, because that's exactly done by this bad function.
This one, there's no errors and must fail.
Yes, I think so. Let's try again. Yeah.
Okay. Okay. So all the changes make sense, like everyone else?
It makes sense to me.
Yeah, I know.
Yes.
Has to make sense for the students. Okay. Yeah, we have no English students, so that's good. Actually, we have this unless in the stablecoin tests.
Yes, we use unless the locker as well. Yeah.
My meet once. So okay. So this is how the library works, but we still need to test an actual contract. So for the contract, we're going to test this negative redeemer that's named, but this is just a validator. This is the whole thing. It takes a custom datum that is a wrapper around the deadline. This is completely unnecessary, but the idea is to show you that how you can use these custom datums with the testing library. And so the validator itself, it takes this deadline and an integer and checks two things. One is that the redeemer has to be negative, basically, and that the deadline has been reached. The redeemer is just that this is the whole test, so it's just the actual number the integer has to be less than 0, and to check the deadline we do, I think Lars already explained this, so we make sure that it contains the transaction is contains from the deadline up until infinity. so that has to be the valid range of the function. So
I think that's exactly the same as I explained in the vesting contract, the same condition.
perfect.
Like last, yeah.
Yes. Perfect. So we have this, we have to reach the deadline, and after the deadline, we have to provide a redeemer that is negative. That's any other combination of redeemer and datum is wrong. So we want to test this. To test this, we have this unit testing redeemer. Sorry, let's go here. So same procedure as before. The test group, test validation, some sensitive values. We have two that we expect to be okay. We use this good. As you can see, this kind of like boilerplate stuff, this is always the same, unless you need more money. So we expect 4 of the tests to go wrong and 2 to go right. So let's see. So user 1 logs, always user 1 logs, that's not irrelevant. User 2 takes, and we test first that the redeemer is negative, the 0 are positive, all 3 after the deadline, and then we check the same thing, negative, 0, and positive, but before the deadline. And to do that, we use the like all tests are the same test script, like it's the same test with different parameters. It takes first the POSIX time. This POSIX time is the deadline, and second takes the the first time is the datum, the second one is the redeemer, basically. And we provide, this is the quite important hard-coded value. That is the time we wait until we consume the, we try to consume the UTXO in the script. So we're going to wait until POSIX time 1000. So that's always going to be the case. So what it changes, to make the text work, what we change is the deadline we pass to the contract when we generate it. The first 3 are 50, smaller than 1000. So the deadline passed by the time it's 1000, and the other 3 is 5000. So we are trying to consume before the deadline has been reached. Let's see. We have the same set of users as before. In this case, we just need 2, so just 2. Then we have the valid scripts, the validation script. In this case, as you can see on chain, if we go to on chain, is the actual redeemer, the actual validator that we just explained. So let's go to the top. We are importing the actual validator and name it on chain, just in case if you want to use the same to test different stuff. So we take the validator and pass it through this make type validator to get the typed validator type that the Bluetooth model needs to work. And now we have our validator script. Now we can start creating the transactions. We're going to create a login transaction. And
Robertino, sorry, there was a question from Jason. Could you explain why smaller POSIX time means a later time?
Yes.
It doesn't. I mean, the point is, I mean, he always waits 1000, I don't know, milliseconds or seconds.
Yes.
And so a smaller deadline, I mean, if the deadline is 50, then if he waits 1000, then he will be after the deadline. But if the deadline is 5000 and he waits 1000, then he's still before the deadline. So by having because the time he waits is fixed. So if he makes the deadline farther in the future, it means that his transaction comes before the deadline. So that's why it's the wrong way around, basically. Does that answer that?
Yes.
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 Good,
So like,
good.
that's the deadline. So if I consume it, always consume it at 1,000, and the deadline was before, it makes sense. If not, it gets rejected. So this means deadline, and this is the time when I consume. It's kind of maybe counterintuitive because one would think that the deadline is fixed and the time I consume it changes, but it's easy to code it this way. So we have two helper functions to create transactions. We have to lock the UTXO at the script, and we have to consume it. So we create these transactions that we're going to see where these values come from when we actually use them. But for now, we provide the locking transaction with the deadline. We provide this user spend value and the actual value that we want to lock. This user spend value, as you can see, we're using it right here. Okay, this user spend is the UTXOs the user has to spend to be able to perform the transaction. So that is dependent on the current state of the blockchain. So there's no way to hard code that. So we pass it as parameter. And as you can see, we're returning a transaction, and we are using mconcat because the transactions are monoidal values. So we can combine them we combine lists of them using mconcat. So we have two transactions, the transactions that the user has to spend the UTXO and get the change, and the transaction that someone has to pay to the script. Which script? The validator script that we just defined in line 54, 55. And we have to provide the datum. As you can see, in value, as you can see, validator script, pay to script takes a script that's as the type that is an instance of has datum and has address. So like our script as the first parameter, the datum as second parameter, and the value that we want to pay to the script as third parameter. So we already have the script. We already have the type of the datum as well. We can import it straight from our validator. So we can just apply the make custom datum constructor to our POSIX time, and then hash the datum. And finally, we log whatever value we want to log. That's also a parameter. And then in the consuming transaction is the other way around. We want to spend from the script, and we want to pay to the user. What we want to spend from the script, is the same script, so we provided the same as before. We provide the reference of the UTXO we want to consume from that script. Then we have to provide a redeemer, and the redeemer we typed as integer, but the untyped validator takes built-in data, so we use this make mki to transfer the integer to built-in data. So we have our redeemer there, and we have our datum here. So we provide all the values needed to be able to spend the script. And once we unlock that value, we have to tell the transaction where that value should go. So we use the pay to key to say, I want the transaction to create a UTXO at this user key of this value. With this value is the same amount that the value we are unlocking. So this is the consuming transaction. And now we can actually write the test, which is that's it. That's the whole thing. And here we have the unless at the end. So we take the POSIX time and the integer as parameters. Let me go to the top. These two parameters, POSIX time and the integer, to test each of the variables we want, each of the permutations we want to test. And we start the procedures. We have to create transactions. So we set up the users, same as in the previous example. Then we want the user 1 to log 100 Lovelaces in the validator. For that, we create the value. We use this ADA-value function that takes an integer and returns a value containing 100 Lovelaces. Then we use this spend function that takes the cookie hash and a value and returns what we said before, returns the UTXOs that the user has to spend to be able to perform the transaction. This is dependent on the previous state of the blockchain. So we do it here. Then once we have the UTXOs we have to spend to be able to make the transaction, we submit the transaction. The submit transaction takes a cookie hash, the person that wants to submit the transaction, and the actual transaction, and submit this to the blockchain, meaning updates the state. User one wants to update it and wants to log the transaction. We have to provide the datum that we pass as a parameter. We want to provide the spending transaction and the value, that the value is the one we hard-coded here. This could be also something that varies, but because the validator doesn't really check the value itself, the value that has to be is just checks. The check depends on the time and the redeemer. This is not something we're interested in, so we just hard-code it. So the user one submits the transaction, and then we have to wait for a bit. We have to wait until the deadline of 1,000 POSIX time we said before. And then the user can try to consume the transaction, consume the UTXO. So the first thing we do is to query the UTXO. We have this UTXO add function that takes, here says user, but it's any type that has an address. So, and we know the scripts have addresses, so we can apply the UTXO at our validator and get all the UTXOs. It's a list of UTXOs sitting at that address. We can pattern match to extract the first and only UTXO. We know that it's only one because we just created a UTXO. It shouldn't be any other than one. And then we have something new here. So we said that the transaction have to be valid in a certain time range. So when we construct the transaction, we have to specify that current time range. And in this case, we use this current time radius that we provide a POSIX time, in this case is 100. And it creates an interval of a radius, of equal radius around the current time of the blockchain. So in this case, this current time, this time range is going to be between 900 and 1100 POSIX time. So using everything we built so far, getting the reference and the UTXOs and the current time, we can create the consuming transaction right here. So we create the consuming transaction, we provide the datum, we provide the redeemer, the user that wants to get the money after the transaction, the reference of the output we want to unlock, and the value locked at the TX out value. So using those, let's go to the definition just in case. So when we spend the script, we need the reference, we need the redeemer, and we need the datum. And when we pay to the user, we need to know the value we are paying to the user. And which user, of course. So once we do that, we build a transaction, but we have to make sure that that transaction has to be validated in a time range we proposed. And then we submit the transaction. We update the state of the blockchain to submit the transaction. And that will be it. That's all the things we wanted to do. User 1 locks, user 2 tries to unlock. Because we have these variables here, we have the datum and the redeemer that change depending on how on the test. Sometimes this will fail, sometimes this will be okay, but we have to perform the checks. So we check, we extract, we use this value add function that takes an address and returns the value locked in that address. And we map this value add to the two users. So we have the value of both users. And we check that user 1 has 900 and user 2 has 1100. And we log errors if that's not the case. So that will be it. If we run the tests, about test, and in this case is unit testing negative redeemer time. Everything passes, wonderful. And just to prove that if something is wrong, we can just, for example, make this equal to 0. And now, what do you think? Anyone wants to guess which is going to go wrong? All of them, half of them, one?
I know.
I know you know. There you go. Oh, someone answered. So let's hide this. All except the second. Good guess, but not quite, but good guess. So only one is going to fail. The second one is going to fail. I mean, let's see. All except the second. Maybe you were right, actually. I depending on how you interpret it. But yeah, so the first one, sorry, we are testing that the script is less than the redeemer is negative. And after the deadline, that should succeed, but it doesn't succeed because it turns out that it has to be exactly 0, nor negative. So this one fails, and it's supposed to go well. All the other ones, even though we change the definition, for example, all these ones that are using 42 as well, those didn't broke because we are checking that it fails. We are assuming that this will fail from the get-go. We thought that the failure was due to the deadline, but it's also now due to the number being different than 0. So this is just a reminder to make sure to test all the possibilities, all the combinations, because you have to make sure that if it fails for the reason you think it fails and not for other reasons. And this is the perfect transition to talk about property testing. No, I signed out. 1 second. No one can see me right now.
Yeah.
Okay.
Maybe why I just wanted to, I mean, you mentioned briefly that there's this wrapper for Atlas around Pluto Simple Model. I just wanted to say, I mean, point out two things with this. I mean, one is it doesn't, I mean, it's not very faithful to the real blockchain. I mean, in certain regards it is, but for example, it doesn't do transaction fees and it doesn't do these min deposits. I mean, you were sending around 1,000 loveless. On the real blockchain, you can't because there's this min deposit, which is like around 1 ADA in that case. So you could never send like 1,000 loveless to a user. You must always send at least 1 ADA plus something. And I mean, as you saw in your checks, I mean, you got these precise values on the real blockchain. It just wouldn't be precise because of transaction fees. So it would be a bit less than 1,000 or 900 or whatever. That's the one thing. So this Pluto Simple Model doesn't take these things into account. And I think also not timing. I mean, the transactions are there immediately, basically. But anyway, that's not so important. And the second thing is, I mean, you basically have to learn a new API. I mean, you had I mean, when you constructed your transactions, it was this send to user key and spend from script and those things, which is like a new thing that you have to learn on top of everything else. So that means, I mean, if you wanted to do this for real, I mean, your contract, if you now wanted a real implementation of that, for example, using Atlas, you would have to write two versions of your off-chain code. One that you now did for the Pluto Simple Model for the tests, and then one, for example, using Atlas for the real thing. And it's, I mean, sort of similar, right? I mean, you had things like spend from script or must pay to script. And in Atlas, we have things like must have output, must have input. So it's similar, but not the same. So you basically have two versions of off-chain code. And then, of course, there can be the problem that they don't agree. So in your test, you basically the transactions you construct are different to the ones you use in your production system. So that means that maybe the test tests something that's not what you're actually doing. And this Atlas integration of Pluto Simple Model addresses those two problems with the transaction fees and min deposits, and also with that you have to basically duplicate your off-chain code. So if you use this wrapper for Atlas of Pluto Simple Model, you can just write your off-chain code once. Maybe you have been wondering why we had this weird monad constraint, this GYTX query monad or GYTX monad, and didn't just use a concrete monad. And the reason is exactly to be able to do something like that. So we could use the very same off-chain code that we also want to use in production. And instead then running it on a real node, you can basically convert it into this run monad from Pluto's simple model. So you can use your exact same off-chain code both for production and for creating these test cases. And it uses real transactions. So the way this Atlas thing works is it first constructs a real transaction that you could submit on the actual blockchain, and then translates that into Atlas, into Pluto Simple Model data structures, which has the effect that, for example, transaction fees and min deposits are all checked and authentic and realistic. So I think it's actually better to use that, but nevertheless, I mean, if you're not using Atlas, then of course it's also good. I mean, Pluto Simple Model is still very useful to use standalone like Robertino now does. Yeah, sorry, that was all I wanted to say. Oh, basically what I just said is written there. Okay.
Okay, so
Okay. Shut up now.
No. Should I continue or?
Yes, please.
Yes. Okay. Anyone has any more questions about what we just covered? Unit testing, Pluto Simple Model, because we're going to move to property testing.
I think not so far.
Okay. So let me move this. Where was I? Here. So this is what we have so far. with the test we did, with test we did so far, we cover those 6 points we are seeing right there. So assuming time moves to the right and the value of the redeemer on the y-axis, and assuming the deadline is right in the middle. So we know that if we are before the deadline and the redeemer is negative, it should be, I mean, we don't care about the redeemer. If we are before the deadline, all values should be, all transactions should be denied. If we are after the deadline, the transactions that have positive redeemer should be rejected, but the transactions have a negative redeemer and 0 should be accepted. We know conceptually that that's what we're testing, but what we are actually testing is just these 6 little dots. What we want to test is this. We want to fill the entire plane with tests, and this is like how the end result should look like. It doesn't matter which exact part of the point of the plane we are. We know that if we are in this quadrant, it should be positive, and in any of the other 3 should be negative. The transaction should be rejected. So to make this transition or something as close as possible to this transition, we use quick check to test the properties of the value, not just specific combinations. So we already fixed this. This is ugly, so I'm going to just rerun it just so it's all greens. And if we open property testing, negative redeemer, we have just 3 properties we want to test. The properties are: before the deadline, it fails. If it's positive, after the deadline, if the redeemer, is positive, but it's after the deadline, it always fails as well. And finally, if the redeemer is negative and it's after the deadline, it should always succeed. Those are the 3 properties we are interested in. The types changed a bit. We have now, instead of returning Boolean or unit, we have property. And we have this test property that comes from quick check. But as you can see at the end, it returns a test tree that you are all familiar with by now. So let's write these 3 tests, these prop _ something tests. We start with a couple of helper functions and instances. The thing with quick check is that we have to be able to, it can only test types that are instances of the testable type class. And because we are using this run wrapper around the state monad, we have to make the run type an instance of the testable type class. This is pretty much like, this is boilerplate. You could consider it boilerplate because once it's done, you literally don't change it. So yeah, here we are assuming that whatever the run returns, it's already a testable type. So we initialize the blockchain with the same values as before, Babbage, and the same amount of ADA. We run the mock chain, and to get this the return type, this A type that we want to return as a property, and we apply the property function that takes anything that is testable and returns a property to this value that returns the run state monad returns. So by doing this instance, we can test our blockchain, our mock chain. And then another thing, maybe we should, let's see. I think, yes, if we quick jump to, here, arbitrary, already saw it. So this arbitrary type class provides random generation and shrinking of values. We already saw this in the Haskell section, but I want to show you that we have this arbitrary method that generates values for a given type. And we have a bunch of instances for arbitrary ASCII strings, a bunch of floats, ints, long, like a bunch of them, float, double, Boolean, char, but we don't have a POSIX one. Sorry, we don't have a POSIX time one. So we have to create that one. And for that, we have to implement the arbitrary. We have to implement the arbitrary method. We're going to use this choose function. If we choose, that generates a random element in the given inclusive range. So we can define the maximum and the minimum value. And it has to, we have to use a type that is an instance of random. As it turns out, integer is an instance of random. So we can generate random integers between 0 and 2000. This is just an integer, random choose integer. And then we wrap this integer in the POSIX time constructor. That is the constructor from the Bluetooth Ledger API that returns the POSIX time that we needed all along. So in using this instance, by creating this instance, we just made POSIX time an instance of arbitrary, and now we can generate random POSIX times between 0 and 2000. So these two instances will help us generate the values and test them. Then we go to the same ones as before, way before consuming 1000. Set up the users. We just need 2 users in this case. We're going to wait the same time, so it's the same dynamic as the previous one. Then we start with the validator script. Same validator. We use same import for the same validator. The locking transaction is the same one. I think it didn't change at all. Consuming transaction didn't change at all. And now we start with the testing properties. So we have another level of abstraction with the run checks function that I create down below. But as you can see, like same as before, we previously have this test script function that took all the parameters, but the tests were the same with different parameters. Well, in this case, the tests are kind of the same run checks test, but in this case, we say we provide a Boolean saying if this test should pass or not, and the datum and the redeemer. So in this case, we're checking if before the deadline should fail, so it falls. After the deadline should fail, after positive, after the deadline should fall, and negative should pass. And we already saw this, but just in case, so we are going to take, if we go to the top here, all properties take 2 parameters, but we're not specifying them. That's because quick check is going to fill that void for us. It's going to generate values and provide it for us. So we have control over which ranges, or we have further control than that, but we are going, in this case, control the ranges of these values. So now at this point, we have to assume that quick check is going to give me random values of POSIX time, in this case, between 0 and 2000 POSIX, and random integer values. I didn't have to specify the arbitrary instance because already an instance integer. But we don't want any value from 0 and 2000. In this case, we want the values to be, we want the deadline, only the deadline that are bigger than the time what we are consuming. We're going to try to consume the transaction at POSIX time 1000. So if the deadline is bigger than 1000 or 1001, this should never fail. This should always fail because we're always consuming before the deadline. That's why we are filtering all the deadlines that are bigger than, so only the deadlines that are bigger than 1000. In the positive, but we don't filter anything else because we don't care about the redeemer at this point. It can be positive, negative, we don't care. We also have, in this case, the positive after. In this case, we want to make sure that it's positive, and we want to make sure that the deadline is less than the time we are consuming. So we are applying these two filters to whatever value quick check randomly generates. And finally, we apply the inverse of the redeemer. We want that the redeemer is only negative and that the deadline already is smaller than the time we are consuming. So these are the only difference between the checks, the filtering of the values we provide. And then we run the checks. Let's see. No, let's go. I think it's ordered. Yes, it's correctly ordered. So we want to run the checks. Let me just repeat. So we have to do a bit of extra steps. This is what we actually when we actually test, but because we are testing a monad, we have to add this monadic property check, these monadic property values before the check. So in this case, we are going to, this test values is the function that actually performs the test like we used to so far. But we provide the three parameters we talked before. If should consume tells me if I should be able to consume the UTXO. And we provide the deadline and the redeemer. And so then we run the property and we get if the balances match. And in this case, we assert that the balances should match. This is going to be part of the test values. And if that's all well, the test passes. So that's it. I deleted something that we had before that I'm going to add later. But for now, let's leave it like this. So, and now this is the actual test. This is pretty much the same as before, because like all the new stuff we already saw. So we have to know if we should be able to consume the datum and the redeemer. We set up the users, create the value, get the spend, submit the transactions, all the same, wait until the time. Now, this is a bit more interesting. We get the UTXO that the validator script. We know that it's only one, so we pattern match to extract it. And then we create another two let bindings because We're going to use it a couple of times, but this is the same. So as say the same conceptual as before, we create the consuming transaction. The consuming transaction takes the date, the redeemer, the user, same as before, and we get this transaction. And then we get the expected value of the second user. The expected value of the second user is that if it should be able to consume the UTXO at the script address, then the user should have 1100 Lovelaces. Else the user should have 1000, because it has 1000 from the get-go and doesn't change anything. So this is why we pass this should consume, to make sure that we have the correct value at the end, and we can expect the correct value at the end. And we create the radius for the time, same as before. The transaction has to validate in this time and these properties of the transaction. If it should consume, then we submit the transaction, and that's it. If it should be able to consume it, we just submit the transaction and all good. But if it shouldn't be able to consume, we also submit the transaction, but we expect that it should fail. So we are integrating all the two branches into the test itself. Then we check the final balances. This is same as before. The value, and we return. We checked the value of the first user is always 900, because you don't need permission from no one to send a UTXO to some address. So that's always going to pass. But the user 2, the expected value is going to change depending on the actual parameters we're going to pass. And this is what we return right here. This balances match is the Boolean that we return right here, and we assert that it has to be true. And those are the checks. So if we run this, perfect. So as you can see, anything before the deadline always fails. It passes. 100 tests, we could change 100 to 10,000 to be more sure about it. We discarded 92. This discarded happened right here. This is when we discard. Quick check gives me 900 of deadline, and at this point I compare and I discard 900 and I go back and ask for a new one. So that's all the discarded here, here, and here. But as you can see, the 3 tests passed as we expected. And let's see, if we go to the run checks function, that I just deleted something. And why I just deleted was that I'm not sure, I don't recall if we already did this, but you can collect information about the tests while running that. You can ask a quick check to collect information about the tests. And in this case, we want to collect the redeemer that is being provided, and we extract the POSIX time, the actual integer, from the deadline. So we're collecting this, and now if we rerun the test, quick check is going to provide us with a bit more information about what exactly has been tested. All 3 test passes, but if we go to the top, and anything before the deadline always fails. So 100 passes, 88 were discarded. And as you can see, the filters we had for the first check were that the deadline had to be bigger than 1,001. So the redeemer can be negative, 0, or positive. We don't care, but the deadline is always bigger than 1,000. POS6 time. Positive redeemer after the deadline always fails. So this one has to be positive, and the deadline, because we consume 1,000, the deadline has to always be smaller than 1,000. So positive and smaller than 1,000, everything. This one went a bit close to the limit. That's good. And as you can see, the tests were successfully, the values were successfully filtered. And the final one, same as before, this had to be less than 1,000, this one negative, and it is perfect. So this is how we can test. I think I wanted to say something else, but I don't remember right now exactly what I wanted to say. Anyone has any questions? In the meantime, I try to remember what I wanted to say. Yes, we have.
Yes, we have a question.
Is there a case where unit testing is better? Conceptually, I don't think so. But in practice, there are some cases when property testing is heavily limited, because like the amount of resources you need to use doesn't make it, it's not possible to actually run 1,000 times the same test with different variables, etc. But maybe this is something Lars knows more about.
I mean, as I explained when we talked about quick check, unit tests are a special case. If you have a quick check test without parameters, I mean, where it's just of type property or Boolean, doesn't take any arguments, then that is a unit test. So so strictly speaking, property-based tests are clearly more powerful because they include unit tests as a special case. But as you say, I mean, in practice, I mean, with unit tests, I mean, you can maybe using your own intelligence can come up with some edge cases that by randomly generating tests you don't find. But I think in practice, I mean, at least according to John Hughes, for example, the inventor of QuickCheck, actually it's much better. I mean, randomly generating test cases is much better in finding weird edge cases than you are. So I think property-based testing is basically always better. It's just, but of course, I mean, it might be more effort. So it's of course always a trade-off how much time and money you are willing to spend on tests. But in general, they are always better, I think.
Okay, so let's see. Yeah, there are two things that I wanted to see. I wanted to break this to show you, and this is the other one that I just recall. Maybe you will think that this limitation is unnecessary because we are already filtering the values here. But this limitation when generating the values is highly important, because if you, for example, try to make it bigger, the options that QuickCheck has to generate a value are so much bigger. Let's see. 2 out of 3 test phases scale are so QuickCheck has so many options that it's going to try to select a bunch of values that are and we're going to keep filtering, keep filtering, keep filtering. So at some point, QuickCheck is going to just give up, say, okay, we passed 0 tests and we discarded 1,000 tests. You are too picky with the filters. And that could be two different things. Maybe you are filtering both sides of the equation. You are filtering this and like the inverse, the less than. So you are virtually filtering everything. But that error is a bit more obvious. But the actual error here is that we are giving too much leeway in the numbers to choose in the arbitrary instance. So QuickCheck is way more likely to pick numbers bigger than 1,000 because it has way more surface area to pick from bigger numbers bigger than 1,000 that's smaller, that between 0 and 1,000. So that's why we want to limit the amount of the range into a sensible range to allow to QuickCheck to be more likely to pick a value we are not going to filter. And maybe if you want, we can just change the redeemer to be less or equal than 30. So now the property that the property positive redeemer after the deadline always fails, this should not be true. These properties should not be true anymore. So let's run it. And indeed, QuickCheck found a counter example. A session failed, POSIX time 850, and where is the redeemer?
The
Redeemer
next
one.
line, the one, yes.
Yes, thank you. Here's the redeemer. We tried with the redeemer. We told QuickCheck that the redeemer, any positive redeemer should fail, and QuickCheck found that there is a positive one that didn't, so it stopped looking after that. We have a question?
We have a question, yeah.
What happens if it was for a first condition? No, that, yes. Samsung, what happens if we swap 1,001 for 1,000 in the first condition? That shouldn't change anything. I think there was a quirk. There was a quirk in the previous version. There was a quirk in the previous version when the ranges were a bit sketchy, but I think that was already solved a while ago. So if we can change this 1,000 and we have to fix our redeemer. And if we run now, it should still work. Yeah. So that was in previous lessons, the versions of Pluto Simple Mode, there was a quirk about that, but it's already been solved. So we are going to use this, so it's easier to understand. Awesome, thank you. Perfect, amazing. So I think we already covered what I wanted to talk about testing. We have the homework that I wanted to give you all. Maybe I should, I'm going to explain that and then we can take a break. So we have this interesting, exploitable swap here. So we have this interesting validator. That is what I mean, we already talked about this in the previous lesson. So this is a validator to sell a token. And so you have in the datum, the beneficiary and the minimum price you are willing to accept for the token. And then you have a validator that takes this datum and checks that the beneficiary in the datum, that means the person that is selling the token or tokens, is being paid. And in this output to beneficiary, we check that the value paid to the beneficiary is greater or equal that the amount of ADA specified in the price in the datum. So that's the only check this validator does. Checks that the person is being paid same or equal that is being asked. That's it. But as we explained before, this has a big vulnerability in the case that you sell more than one token, because you can, because I'm just checking that the person in the transaction, the person is getting paid, I can consume 2 tokens, pay the biggest price, but just once, just pay the more expensive and consume both, because both are going to individually checked. Each validator, each UTXO is going to be individually checking if the beneficiary is getting paid. And both of them are going to say, yes, it's fine, the beneficiary is getting paid, so I'm going to release the funds. So the user, the buyer consumes 2 or more tokens for the price of the most expensive one. So this is an exploitable validator. Lars already told you one of the ways that you can fix this is to make sure that you can consume only one. And another way you can fix this is to add another parameter called tag that can be an integer or a bytemap or whatever that uniquely identifies the output. Either of those two are fine, but what I'm going to ask is to write the test to catch this vulnerability. So I already pre-written something for you. We have the normal spending should be good, double spending is bad. So we have this super cool token. We're creating a fake coin called super cool token. And we have the script. We have this scrub script. This is just a type synonym to not having this. This is the homework script, what we just saw. And now you have to write the login transaction, the consuming transaction, and the double consuming transaction, and actually write the 2 tests, the normal spending and double spending test. You already know everything needed to write this test. After writing this test and making sure that they catch the vulnerability, you have to fix the exploitable swap and make sure that the test doesn't pass anymore. So that's the homework I'm leaving you. After the lesson, we're going to upload this to the repository, and you can do the homework. Any questions about it? Because after this, I think we're going to go to the stablecoin example?
We can wait in.
You can ask
Okay.
later as well, so it's okay. Okay, so let's maybe 15 minutes of break of 15 minutes. Make sense?
Yes, sounds good.
Yes.
Yes. Okay. See you, everyone.
See you. Yeah.
Okay, so we had one question during the break. Could you give a hypothetical smart contract design that can help an online store sell Nike shoes across the globe? Like, how will this whole smart contract setup work? So I don't think that's a problem. Like, the biggest problem, I'm guessing, is logistics, not value transfer in that case. But like, for example, if you want to sell 1,000 shoes, you can, let's see, you can take this same contract after fixing it, or actually we can fix it right here. We can say shoe ID and the beneficiary is the store. And then, for example, you can mint 1,000 you can mint 1,000 tokens for each shoe and deploy them using this fixed smart contract. Let's see. And then just ask for each person. You have to have a way to the person to convey the information where you have to send it. But you can say, okay, anyone that has this shoe ID gets the shoe. You just have to ask for it, and I will send it to you. And the only thing that I want to make sure to have is that you have that the ID. And as soon as I create the sending, as soon as I'm about to send the shoe, you have to burn the token, and I will like send the shoes. But I don't think that's a blockchain fitted issue. I don't think that, I mean, that's logistics, and you still have to trust the store. So because I have to trust the store, you can just send them ADA straight right off the bat and like avoid all the smart contract part. So in that regard, I don't think using smart contract is to interact with a centralized entity is I think is overcomplicating the transfer. I mean, the only realistic thing is that you're having troubles charging from people from other country, and in that case, you can just accept ADA in your website, and that's it. That requires no smart contract whatsoever. So I think that's all I'm going to say about that specific use case. But we are going to speak about another more fun and complex use case next. So if you're good with that answer, you don't want anything more, we can move on. Thank you. Okay, perfect. So now, now that we learn about testing, let's see our final super cool example. So we just saw the testing lesson, and now let's talk about stablecoins. So I think before that, I'm going to talk about the concept itself. Let's see. Give me 1 second. I want to search for my diagrams. what we're going to build is going to be, I mean, it's already built. We're going to go over the code so everyone understands the key parts of it. It's long. It's a Next.js front-end app with off-chain code, and there's different validators. So I'm not asking you in an hour and a half, 2 hours to understand everything, but I will try to convey the key parts of the issue. So let's share again. Okay, so I'm going to share this explanation with you in the repository of our course. But this is like the main thing. We want to make not only a stable coin, we want to make a stable coin in Cardano, but also we want to have a way to interact with it. We want to have a way to deploy the stable coin. We want to have a way to create, mint, and burn stablecoin. So for that, we're going to create also a front end to execute and interact with our contracts. I think we should, I'm not sure. Yes, so let's talk about how a collateralized stablecoin works. So the whole point of an algorithmic stablecoin is that instead of having someone you have to trust in charge, some entity or person, you have to trust an algorithm. So the algorithm that has no ulterior motive, that what is already written in code, is the one that is handling the stablecoin. And an algorithm, a collateralized and over-collateralized algorithmic stablecoin means that you have to provide collateral more than a collateral with a more value than the amount you want to mint to get to the stablecoins. So in our example, it's going to be 150%. And we're going to go over the examples, but just as an opening of the statement, just to give you some context, an over-collateralized stablecoins needs that someone has to provide some amount of collateral that is valued as more as the amount of stablecoins in the wild, like everywhere. Cardano uses native tokens, so once you have minted, you have the contract has no longer control over what's going on with the stablecoin. So you have to take into account that as well. That might be harder for people that have worked with Ethereum previously to understand, but is easily solvable. So that's what we're going to build. We're going to go over the diagrams that explain how each contract works and how we are going to actually perform all this interface, all these transactions. Then we're going to go to actually use the front-end code, so you can see how it looks in practice. I think that's the most fun part. Hopefully that makes the click. And then we're going to go over the on-chain and off-chain code. So to deploy a stablecoin, our stablecoin is going to need one oracle. The oracle is going to provide the relationship between ADA and some other currency. We chose to be US dollar, but you can do that's up to you. Whatever you want to track, whichever value you want to track is the value you have to put the relationship with. We're going to try to peg our stablecoin to the US dollar. So our oracle is going to provide the rate of USD ADA. Then we need a validator to hold the collateral. This validator is going to lock the collateral, and you can only unlock it in a specific scenario. We have to burn the specific stablecoins that were minted before, etc. So that we're going to go over that as well. But we need some sort of validator. We need a validator that takes into account that the user has to provide proof of certain parameters, so the user can get the collateral back. So this validator is going to lock the collateral. And finally, the most complex of our contracts is going to be the minting policy. We already saw one in the previous lesson, but minting policies, the only thing, they don't lock value, they don't restrict the consumption of UTXO, but they create and delete the mints and burn will be the equivalents tokens in the blockchain. So that's their job. And we're going to actually use two different, one to create NFTs and one to create the actual stablecoins. So let's go over a bit of the transactions that we want to do. So this is the first transaction. Let's see if we can now copy. Can we zoom in? Yes. So this is the first thing we need to do to deploy our Oracle. So, I mean, this tutorial, this lesson contains another lesson inside that is about how to create oracles and use oracles. So that's like plus. And so to deploy your own oracle, you need a way to track which UTXO in the blockchain is the one you created. We talked about this yesterday, but we're going to go over it again because this is really important. Anyone can create outputs in any address. So you need a way to make sure that the output you're using is the one you created, because someone else can create an output in the Oracle address. And if you read any output of that address, you can be easily mistaken into creating the value of the USD ADA rate is different than the actual value, and people can take advantage of that, or it could just break by itself, basically. So these circles represent UTXOs and the rectangles represent transactions. So first, the stablecoin developer, the address of the stablecoin developer is going to mint an NFT. So after the transaction, the stablecoin developer is going to have an NFT in its wallet. Once we have the NFT, we're going to deploy the Oracle. We're going to provide the NFT and the current USD ADA rate. And we are going to provide these two parameters, these values and this parameter to the deploy Oracle to create an UTXO at the Oracle validator address with the USD ADA rate in its datum and the NFT as a value. So from now on, I'm going to filter all the UTXOs in the Oracle's validator to only the only one that has the NFT that I created. And once I find it, I'm going to read the USD ADA rate in its datum and perform calculations based on that. And the other output of this deploy Oracle transaction is the stablecoin developer without the NFT. So this is how we deploy an Oracle. After that, in this case, after that, we also have to deploy our collateral and our minting policy validators. This is something we didn't cover so far. This is some new capabilities thanks to Basil hard fork, that now we can not only consume and create UTXOs, but we can also reference them. The key difference being that you can read values or run scripts in a UTXO without actually consuming them. So you can just deploy and you can attach the collateral. In this case, we in the deploy collateral and minting policy as reference scripts. The stablecoin developer is going to create a UTXO somewhere in some address that has the collateral validator attached to it, and in another output in some address that has the minting policy attached to it. So it's not the minting policy's address or the collateral validator address that we were creating UTXO on. Is somewhere else, but we are attaching the actual validator in the output. That's the key difference between when we create scripts to be referenced and we create outputs in a specific script. In this case, in the example, we are creating a UTXO in the always false validator. This is in the example we are saying, okay, if we deploy our contracts, if we create the reference scripts in the always false validator, our users can be 100% sure that there's no way we can change them. Because no one can consume from the always false validator. It never unlocks. So that's one way that we could go over this. Another way, that is the way that we actually do this in the example, because it's easier to manage, is to deploy to our own wallet. In this case, like in practice, I'm not advising this, but in practice, the stablecoin developer is going to deploy the oracles in its own wallet. So I'm going to have the stablecoin developer is going to have the collateral validator in the minting policy's own address. That's like the worst thing you could do in real world, because this is going to be attached to UTXOs, and then the stablecoin developer wallet is going to make some transaction, and it's going to consume the UTXO that has these validators attached to pay for the transaction, and all of a sudden you lost the script. So that's a whole thing. So, but we are going to do it because I have different wallets for different users, and it's easier to redo everything. But in practice, one of the recommended ways will be to use the always false validator or some other validator that you are sure that it's not going to be consumed without you or your users wanting to. So at this point, we already deployed both validators. We don't have any UTXOs at the actual addresses, but the validators are on the blockchain. So from now on, we can reference them to create transactions. As soon as we created the oracle, it's going to be outdated. So we need also a way to update the oracle, the value of the oracle. As you know, the rate of USD ADA varies tremendously. So we need a way to update the value in the datum. So in that case, the stablecoin developer is going to consume, in this case, it's going to consume the UTXO that contains the datum and the NFT, and it's going to create a new UTXO at the Oracle validator address with the new rate. Now, in the update Oracle, we are consuming and creating, and we are taking this NFT and moving it into the new Oracle. When we are actually going to use the Oracle, we're not going to consume it, we're just going to reference it. It's going to be a reference input, not a reference script. The reference input, you can use it to read the values, and the reference script is you indicate that the script that you are referencing has to return true, has to validate the transactions for the transactions to be accepted. That's also a key difference. So we have a way to update the Oracle. Now, let's talk about the different scenarios. So one scenario, you cannot see its entire, well, let's see. I think it's better to just outside. Yeah. So one scenario is to mint the stablecoin. Anyone that has any questions, please ask, because this part is the key to understanding, because then in the UI you don't see the actual transactions, you just see signing and things appear. So now we have everything in the blockchain to actually start minting and burning stablecoins, right? So to mint stablecoins, user one is going to provide a collateral. It's going to be in ADA. That can also be a different thing, but in this case, we're going to provide the collateral in ADA. We're going to reference the script in the minting policy in the always false validator. We're going to reference the script, and we are going to reference the oracle. We are going to reference the value of the oracle to read it. So in these mint stablecoin transactions, the minting policy is going to take the collateral of the user, is going to take the value provided by the oracle, and it's going to make a decision. So it's going to make a decision not only about the inputs, the collateral and the oracle, but also about the outputs. The minting policy is going to make sure that you are creating an output at the collateral validator containing the collateral that you provided as you provide as input, as a value in the UTXO, and as datum. You have to leave it's going to check that you write the collateral owner, and this owner has to be the same pubkey hash as user one. And the amount of stablecoins minted has to be exactly the same amount of stablecoins that user one is going to get after the transaction. Those are the checks that the mint stablecoin, let's see this, the mint stablecoin validator does. Makes sense? We have the minting policy, the collateral, and the oracle validator as inputs. The minting policy checks that we generate this output with the same collateral owner as this one, and with the same amount as we minted in the collateral validator, locking the collateral. And at that point, the user already has the stablecoins and can do whatever he wants with the stablecoins. They are theirs, and that's it. The amount of stablecoins, of course, depends on the datum and the rate where we are going to set. Let's see.
We have a question.
Why is the minting policy in an always false validator? This is because the minting policy, if the minting policy is attached to an UTXO is some validator. We can put it wherever we want, but as a user, if I'm a user of your stablecoin, I will be more confident that there's no fishy work behind the scenes if the minting policy is in the always false validator, because there's no way you can change. You cannot delete the minting policy from the blockchain. You cannot consume that output. So I'm sure that I will always be able to mint and burn my stablecoins as long as that minting policy is there. That's why one of the ways is to you put your reference scripts in the always false validator. Make sense? Okay.
Yes,
perfect.
Thank you.
So we minted our stablecoins. The amount of stablecoins minted depends on the collateral provided and the rate of ADA, USD ADA. So because my stablecoins are tracking the USD, the US dollar, for example, if I set the collateral percentage of collateral of 150%, so I have to lock 150% the amount of value that I mint, and the USD and one ADA is worth $1, so 1-to-1 the rate. If I provide 150 ADA as collateral, I can at most mint 100 stablecoins, 100 USDKs, right? So that's important because the minting policy needs the Oracle to know what's the maximum value you can mint. After the stablecoins were minted, we also have to be able to burn them. In this case, the burning, it's simpler conceptually, but requires one more validator, which is we are trying to consume something in the collateral validator. So we need to actually know the script to run it. So that's why we reference the collateral validator as well. In the minting section, we didn't need the collateral validator because we are creating an output. We only need the validator to consume, not to create. Now, to burn the stablecoin, the user one has to provide the stablecoins. This amount of stablecoins has to be the same amount stated in the datum of the collateral validator's output, the one that we are trying to unlock. So if I minted 100, I have to burn 100, else the validator won't be unlocked, won't unlock the UTXO. And the collateral owner has to be the same one that locked the collateral. So user one is the only one that can provide these stablecoins. No one else can provide these stablecoins to unlock the collateral. So we provide the UTXO to unlock, we provide the stablecoins to burn, and the two reference scripts. Notice that we don't need Oracle because we don't care what is the current value or the current rate. We only care that we are burning the same amount of stablecoins. We are burning these stablecoins is the same amount that we minted in the start. So at the end, it's a zero-sum transaction, a set of transactions. So these transactions unlocks the collateral, burns the stable coins, and after the transaction, the only thing that is left is the collateral at the user one wallet. These scripts have been referenced, so they didn't get consumed, and we can use it later. That's how you burn. And now the most interesting of all is when you liquidate someone else's position. This might get a bit hairy. I think I can. No, I cannot. Yeah, I mean, let me know if you cannot see, but this is the liquidate stablecoin. So we mint the stablecoin based on the rates of USD and ADA, but how do we make sure that that stablecoin is actually stable? Because like if we mint and that's it, the value of the stablecoin, I mean, there's no reason for people to mint, and there's no reason for people to burn the stablecoin. There's just no intrinsic incentive for which people are going to maintain the peg. It's going to interact with the stablecoin to maintain the peg. So to provide that incentive, we allow users to liquidate position of other users. If you mean, like, it's following the same example as before, we have 150% of collateral, so, and the value of ADA is $1, one ADA, so we lock 100 ADA and we get, we lock 150 ADA and we get 100 stablecoins. Now, if the price of ADA drops to 90 cents instead of $1, all of a sudden the collateral we locked is not 150, is less. So the value of the stable coin just dropped the same percentage. To allow to provide a mechanism for people to maintain the peg, in that case, when your collateral drops below the threshold, in this case we chose 150, but that's a parameter, you can change it to 800 or 600. Real stablecoins use parameter much higher than that, than 150. So in that case, for example, user 1 that minted this 100 stablecoin and locked 100, the value dropped, and now the collateral is 130%. So in that case, user 2 can mint its own stablecoins with the correct collateral, because now the minting policy is going to use the new rate. So it's going to be able to, it's going to ask for more ADA for the same amount, mints the collateral, and now user 2 with his own stablecoins is going to liquidate user 1's position. Is going to give user 2 is going to provide 100. We're following the same example as before, 100 stablecoins, because user 1 minted 100 stablecoins. And if it unlocks the collateral, user 2 gets 30% on top of the value it burned. The user 2 burned 100, the equivalent value of $100 in stablecoins, to get the equivalent value of $130 with unlocked collateral. So that's how we maintain the peg in this specific algorithm. This is a primitive algorithm, and there are plenty of ways you can make it better, but it's good enough to create a basic stablecoin. So if the price of ADA falls, people have the incentive of minting stablecoins to liquidate other people's position, and when it goes up, people have the incentive to mint more ADA, mint more stablecoins for the same amount of ADA. So in that regard, that's how the mechanism will work to maintain the peg. So in the case you are liquidating someone else's position, in this example, user 2 is liquidating user 1's position. User 2 provides the same amount of stablecoins as user 1 provided when he minted stablecoins. She minted the stablecoins, and provides user 2, the transaction needs the oracle now to liquidate. Notice that to burn we didn't care. The only thing we care was that the amount of minted was the same as the stablecoins, and that the owner was user 1, the same owner that minted. That's it. But to liquidate, we have to make sure that the collateral dropped below the threshold. And for that, we need the rate. We need the USD ADA rate to make sure that we are below the threshold when user 1 is protected and no one can take its collateral. If the value of collateral dropped below the threshold indicated by calculating the collateral, calculating the threshold based on the collateral and the rate. If the value drop below, user 2 can provide the same amount of stablecoins meeting here, and it is going to take users 1's collateral. That's the most complicated of all transactions. And that's how we are going to maintain the peg. And finally, there is one possible case, that is the stablecoin developer has control over the oracle. That's on its own a bad thing. Usually you want the oracle to be decentralized, but in this case, we're going to say, okay, we trust the stablecoin developer to provide the correct value, but the stablecoin developer, the same as he can update the oracle, he could also potentially delete the oracle. We're going to give the stablecoin developer the option to call it quits and say, okay, I don't want to work with this anymore. This is too hard. I'm going to become a woodworker. So I'm going to delete the oracle validator and get the NFT back. In that case, no one can mint more stablecoins. There's no way to mint because you're never going to be able to provide the oracle the datum as reference script, a reference input. There's no way to liquidate someone else's position, but because you need the oracle, but you can always burn your own stablecoins. You can always retire your stablecoins. Okay, the developer doesn't want to work in this anymore, so I'm going to burn my own stablecoins and move on to different stablecoins. Of course, this is all like hypothetical, but the point is that even if you have this relatively complex smart contract design, you can always provide a way for the user to not depend, to not be under the control of the stablecoin owner. If you decentralize the oracle and you provide this way of burning the stablecoins, you're basically pretty much making sure that as a user, the developer cannot all of a sudden change the rules of the game. We're going to make sure about that as well when we create the smart contracts. So I think that's pretty much it, shorten the stablecoin. If you want to like reread, we're going to have this short article available, but that's pretty much how it works. In theory, the transactions, yes, we have a question.
We have a question, yeah.
What does it, yes, perfect, no problem, Tony. So what does it mean to liquidate a position? So in the burning stablecoins, when you mint stablecoins, you lock, when you mint, you take some amount of value that is not related to the stablecoin. This is ADA or can be Ethereum, can be like ETH or whatever, it can be something else. This is some amount of value that you lock to be able to mint the stablecoins. You have to lock this collateral for the script to mint the stablecoins. Now this value is locked. Liquidate means that you are unlocking, that you are removing that collateral from the equation. And in the case of burning the stablecoins, you are liquidating your own position. You are consuming this collateral validator and the stablecoins related to it. So now you are being removed from the game. At least that UTXO and that amount of stablecoins are being removed from the blockchain. So there's no more, those stablecoins disappear forever. And this collateral is not anymore this amount of value that was locked is not anymore related to the mechanism of the stablecoin. Now it's just any value that some user has in the wallet. Now, when we say liquidating someone else's position, we say that we are doing the same. We are burning some amount of stablecoins to unlock some amount of collateral, but now the person that created that UTXO, that locked that collateral, is a different person than the one that is unlocking it. And to be able, like for the developer to allow other person to user 2 to unlock things of user 1 or someone else, the user 1 has to have so little collateral that is below the minimum threshold allowed by the smart contract. If it's above the value, for example, if it's 150%, and I mint 100, but instead of minting 150, instead of locking 150 ADA, I lock 300. I'm over collateralizing. So if the price of ADA falls, but it's still, once you recalculate the real value of the collateral, once you calculate the US dollar value of the collateral is still above 150%, nothing happens because you're still above the threshold, you're secure. And we're going to see an example of how someone that is more that is more cautious provides more collateral than the one that lists at minimum. And so liquidated means unlocking some collateral and burning the related stablecoins to unlock the collateral and getting those stablecoins and those collateral out of the equation of the stablecoin algorithm. Does it make sense, Tony?
Okay, sorry if I could just speak. Yes, it's making sense, but then maybe maybe you could just now finish the. I was following. You could now finish the liquidating part. How exactly you can just finish explaining how now user 2 would benefit from liquidating user 1's position.
Sorry, what was the question?
Okay, I've understood now what liquidating means, and you've already explained how this liquidating algorithm works. But now with that understanding, you could now finish explaining how, because I remember you talked about how, let's say for an example, that user 1 had something like 30 worth of collateral, and then how user 2 would get it. Maybe now tying up with what you're explaining, just finish the whole transactional operation.
Okay, so let's see. I'm not sure if I understood the question. Not sure if Lars or Karina, did you understand the question? So you mean how do we fit this into the entire tab, or
No. Or maybe just simply a quick example. Okay, user 1 has, I don't know, let's say their value, the amount of collateral that they had fell below 150.
Perfect. Right.
Then how? Yeah.
Okay. An example, like a full on the whole
Yes.
set of transactions in order. No problem. I can do that. Okay, perfect. So what I'm going to do is that I'm going to come here to stablecoin. Lecture off chain. Perfect. So here, in the stablecoin, we have several directories. We have the lecture. The lecture is split in off-chain and on-chain code. The on-chain code is the actual like validators and minting policies. We are going to go over it. The off-chain code has installed a folder called frontend that has an Next.js app inside that we can run, and has all the frontend, all the off-chain code needed to actually perform all these transactions. So what we're going to do now is we're going to interact with that application. And if you are do npm install, and npm run dev, we have our application in localhost 3000. So let's go to localhost 3000. Okay, so this is our application. Let's go through the whole set of transactions, like Tony asked for, using like actually creating the transactions in the testnet. I think we're going to use preview, but you can use preprod or you can use mainnet if you want to spend money on it. So we have a couple of wallets depending on who is the person really creating the transactions. So like we said at the very beginning, we need to deploy the Oracle. To get started even, we always need an Oracle. So, and for that, we use the Oracle's wallet. And first we mint the Oracle's NFT. So as you can see, if we go in here, we just have ADA, but if we click Oracle, mint Oracle, we see that we get charged bits, but we get the NFT that we wanted back. So we sign, and I just copy the transaction just in case. But if we wait for a bit, all these steps are going to be done not in a testing, not in a simulated environment, but in the actual testnet. So it takes a bit. We got our Oracle's NFT, perfect. So now that the Oracle has the NFT, we're going to deploy it. We do that. As you can see now, this button doesn't work anymore, and these two don't work as well because we need to deploy the Oracle. And when we deploy the Oracle, we choose the price of ADA in US cents. To make it easy for everyone, I'm going to use 100 to get started. So I'm going to deploy the Oracle. As you can see, I'm losing the NFT. The wallet is losing the NFT, and it's getting paid to the contract address. As you can see, here's the one asset. The NFT is getting paid to the Oracle's address. So if I sign, we wait for a bit, and here we should have the Oracle UTXO that has the NFT. We already have it, and the Oracle's datum, the value that we read in the Oracle's datum, which is 100 US cents per ADA. If we click here, we can see the transaction that created the Oracle. And as you can see, here is my wallet. It ends in 6M3, which is this one. Wallet, it's too small, but 6M3. So my wallet, my Oracle's wallet, consumed the Oracle's NFT and paid for the transaction, and I got the same wallet, 6M3, got the change back, but it created an output containing the Oracle's NFT as a value with a datum of 100. This is the USD ADA rate. It's on the chain right now with the value 100 cents. Now that we have our Oracle deployed, the owner, let's change wallets, the stablecoin owner, we have a different wallet now, can deploy the scripts. Why we have to do it now? Because we can parameterize the contracts based on the Oracle. So in that regard, if we're going to see, I think it's better explained in the actual contracts, but if we parameterize our minting policy based on the collateral validator and the Oracle, and this number, this percentage, we can make everyone can be sure that the value of the stablecoin is going to be always the same. Because if we change the collateral percentage to 149, or if we change the Oracle address or whatever, the actual stablecoin asset class, the policy ID, changes. So now we are minting and burning a different stablecoin. So by parameterizing the minting policy with the collateral validator and the Oracle, and this number, this 150, we're making sure that these stablecoins can never, this set of smart contracts can be never changed. They have to be always the same. That's on purpose. That's good, because we want to make sure as a user, you want to make sure that no one can change your smart contracts all of a sudden without you knowing. So let's mint. Now we are using stablecoin owner. Yeah, let's deploy the scripts. We are, I think it's better to see it in the actual this thing. So in this transaction, there you go. We have all the rest of the values. This is the transaction that deployed the reference scripts, the stablecoin policy ID in hexadecimal, and the stablecoin asset class as well in hexadecimal. And we deployed the minting policy with 150 as minimum locked collateral percentage. So if we go to the transaction, I'm going to close this. It's not here yet. Let's wait for a bit. There you go. So this is the transaction that deployed, that attached the scripts as reference scripts to UTXOs. We sent them, as you can see, the address. Don't mind these two. These are previous tests that I run. So like, imagine there's just this one. This is one of the things that I told you about not using a wallet that you use for something else. Because you can do this. I created a transaction that has nothing to do with previous scripts, and I'm consuming those UTXOs. But it's okay because I'm not using them anymore. But the thing is, like right now, we are just consuming money, basically. And we are getting back the change and in our own address, the stablecoin owner address, that this address is the one that in the diagrams is shown as always false validator. In real world practice, in like a real deployment of a stablecoin, this address likely should be the always false validator. So in this case, we deploy the two contracts. We deploy the minting policy and we deployed the minting policy here, reference script, which is like nothing really interesting. It's just raw data. Reference script, 2 reference scripts, and this is the minting policy. I know this one is the minting policy because it's longer, it's more complex. So you have to, when you create the reference inputs and reference scripts, you have to attach a certain amount of value that depends on the amount of data that has to be stored in the blockchain. So in this case, the minting policy that mints and burns the stable coins it's relatively complex. So you have to lock it with 15 ADA. And the collateral validator, you have to lock it, is a bit less complex, so you have to lock it with 11 ADA. No, this no need. So yeah, these ones are there. The datums are just not interesting. We just want to make sure that this reference script exists, because then we want to reference them later on, which later on is now. So let's switch to the user perspective. And now let's become user 1. So user 1 needs to mint stablecoins. No one has the stablecoins yet, so we have to mint them. In this case, I added inputs to get the collateral UTXO ref and the stablecoin minting policy UTXO ref. But in the real world scenario, you already have this because you deploy this once, but because in this case, everyone, like all of you, are going to try this on your own home, and it's going to be a different, instead of like modifying the code and changing the hard code string every time, I just put inputs, so it's easier. So we need the reference to the UTXO that contains the collateral scripts and the stablecoin script. So we go back to this, we make this BE7E transaction. B7E, I have others because I did this previous times, but in your case, you're just going to have 3, one with the collateral validator, one with the minting policy, and this one that is the return value. So in our case, we have the value here, the transaction value here, and the index of the collateral is 0, and the minting policy is 1. So I already copied this, but I'm doing it again. Collateral, let's paste this, 0, and minting policy 1. Good. So we are just referencing them in our UI. So I'm going to get the reference script UTXO, because now this is just a string in my front end. This can also be done automatically, but I'm going to get the reference script. So this is going to query the blockchain looking for the actual UTXOs. So if I click, this should work. It works, perfect. Now we are able, the front end found these 2 UTXOs, so it allows me to mint my own stablecoins. So let's see. This is my fault, because I should have left the 10 there. So in this first case, we're going to, so going back to the question Tony asked, we deploy the Oracle, we deploy the scripts. Now we have 3 things that we can do. We can mint, we can burn, and we can liquidate someone else's position. Let's mint. So we have everything ready to go. We're going to mint. We put here 150 as collateral. So if we want to mint 10 stable coins pegged to the US dollar, we get 15. We have to lock 15 ADA as collateral based on the current value of the oracle. So let's click on mint. As you can see, I'm losing 15 ADA because I'm locking this in the smart contract, but I'm getting 10 USD Kenya back to my wallet. And the contract of the collateral is the one that gets the 15 ADA. So let's sign. Perfect. So now we have to open this and wait for a bit. Oh, it's already there. Amazing. So we have our stablecoins. Now we can do whatever we want with these stablecoins. But we chose to burn them because we like to spend money on fees. So now that we have these 10 stablecoins, we can, one of the things we can do, I mean, we can use them. That's it. That the whole point was to use the stablecoin in some sort of long-term investment or commitment or whatever, where volatility is it's a big downside. So that's why you care about stablecoins. So maybe you want to use it as an interface to the fiat world. In our case, we're going to burn them. And for that, we need to know the collateral at the UTXO. We need to know the reference of the UTXO at the collateral address that we want to unlock. So in that case, we search for the transaction. This transaction is the one that we use. As you can see, we consume, wait. Okay, good. We consume the users one money, and we created 3 outputs: the change to the same wallet of user one, the 10 USD Kenya at the same wallet of user one, the 2 we have right here, and we created an output of 15 ADA at the collateral's address. And if we explore this inline datum, we see that we have a couple of fields. This is encrypted, so its hash is not available to be read, but this represents, I have to take a look at one is, not sure exactly the order, but one is the owner, the other is the amount, the other is, let's see, what were the amount minted, and the other is a hash. Let's see, I don't want to lie to you, so I'm going to minting HS. What's this? No, this is wrong. Let's go here. Stablecoin on chain minting. Perfect. These are the parameters of the minting policy. So in this case, we have to collateral datum. Perfect. Here, the collateral, this is the output. This is the same as we have here. One is the currency symbol of the minting policy. So we can only use, we are locking for that specific stablecoin, not other coin, not other token, not anything, just the specific, this collateral locks for this specific stablecoin for this specific user. This is the second field. This is the pool key hash of the second user, and this is the amount of stablecoins minted. This is just an integer, the amount of stablecoins minted. So this is the output we generate. This is the datum of the output we generate in the collateral validator, and the value locked by that collateral is this 15 ADA. So this is the actual collateral we are locking to create this transaction, to create this, to mint this minting policy. So now if we want to burn them, we want to get the reference 15 ADA UTXOs. Let's see. This one A3FE88. I think this one is, and in the index 0. This one is, I think. Let's put reference index 0. Let's try to, we want to burn 10 stable coins. Let's try to get the collateral to unlock. Yes, it got the collateral. So far, we didn't do anything. We just find the collateral we want to burn, we want to unlock, and we indicated that we want to burn it. That means that we are the owners, because we are the owners of this collateral. If not, we wouldn't be able to. And we have to provide the 10 stablecoins. We have it right here, so we should be able to provide them. So let's click here, burn and liquidate. And there's an error, and I think I copied about the reference, wrongly the reference. Here, this is an extra. If you look at the console, we can see that the validator failed. And I believe it's because I copied the wrong transaction, the wrong UTXO reference. So now the off-chain code it did so like previous validation and determined that all's good. And we are gaining, if we sign this transaction, we are gaining 14 test ADA, that this is what it was locked at this UTXO, but we're losing 10 USD Kenyas. Sign. And now that's it. And if we can see here, we lost but we unlocked the ADA back. So we were able to mint, we were able to burn. Now let's liquidate someone else's position. So first comes first. Yeah, let's use user 1 again, and let's like mint stablecoins again. The same stablecoins as before, sign. Perfect. And now while we wait, user 1, we're going to switch to user 2. And user 2 is going to mint 50 50 stablecoins. But because he's a really cautious guy, he's going to lock 100 ADA. So the minimum was 75, but user 2 chose to lock more to be more resilient to the drop of the value of ADA. So let's see, I'm user 2. Yes, I'm user 2. I have no stable coins, so I'm going to mint. I'm losing the 100. I'm locking 100. I'm getting 50 USD Kenya. And I'm locking it. I'm locking the ADA into the contract. Sign. And don't worry if you miss. I copy this now and then to just to quickly access, but in any case, you have the history of transactions here of everything. This is, if we filter, actually, can we filter this? Perfect. So we have like the minting NFT, transaction submitted, deploy Oracle with the asset class. So you have like the whole history of transactions you did in the console. Awesome. So user 2 has 50 USD Kenya and user 1 has 10 USD Kenya. The difference is that USD 1 locked at the bare minimum amount of collateral. So what's going to happen is that the Oracle is going to be updated to the price of ADA now is 90 cents. Let's update the Oracle. As you can see, nothing much. Like we see the +1 asset here, but it's actually like the same asset that is being removed and put back again in the same address. Perfect. So now we have to wait a bit here. I see the Oracle's datum 100. So if we wait for a bit, should be 90. And also the UTXO with NFT should change. Let's wait for a bit. Let's go. So if anyone has questions, this is the moment to ask them. Let's explore. Be right. Should already happened. Come on. Okay, let's see what's going on.
It's now, yeah.
Yes, now it changed.
Yeah.
Finally, thank you. It took a bit, but, but now we are on track again. Amazing. So now we fetch the new UTXO that contains the NFT. This is different than before. And the new value of the Oracle is 90 cents dollar. So that means that user 2 will be able to liquidate user 1 because user 2 put more collateral, so it's still in the above the minimum threshold, but user 1 isn't. So if we see that this is the lock-in transaction, This is the locking transaction, and I'm guessing 0. Yeah. So let's unlock this collateral, but we're going to liquidate this time. And user 2 is going to be the one. As you can see, user 1 still has his 10. User 2 has 50 USD Kenya. And if I put this wrong, I just get in the console the error that the amount is wrong and stuff like that. So I'm just going to go to the happy path. But if any of the conditions that I'm saying is wrong, for example, if the user 1 is above the threshold because he put more collateral, this should just isn't going to go through, and that's it. But in this case, that's boring. It doesn't have anything, and that's it. So let's go through the happy path. Now we got the collateral to unlock. And now remember, we are using user 2 and we are unlocking the collateral of user 1.
Could you also unlock less than 10, or does it have to be the full collateral of?
It has to be the full collateral.
Okay, and then earlier when you burn, do you also have to burn everything, or could you burn less?
You have to burn everything. The contract, okay. Yes. I mean, you can do at first it was a bit different. It was a bit more flexible, but the contracts were a bit more complex. So right. Just to simplify it.
Sure. I mean, it still has the essential elements. I suppose with a real world stablecoin, you would probably be able to also do partial burns, I suppose, right?
Yes, yes. Actually, yes. I have a section about limitations and things to go, like things to do to improve it. And that's one of them. One of the limitations is that you have to create and consume like the whole stuff. So if, for example, the price of ADA goes up and you say, okay, I want to mint more because I'm able to mint more, you have to consume everything and create a new UTXO, right? So that's a bit...
normally you would, you wouldn't want to do that. And also, I suppose, I mean, now user 1, he also sees that the price of ADA went down. So, I mean, he can burn everything, but I probably would also like to be able to just top up his collateral, basically, to add a couple of ADA.
In that case, you have to burn your own and consume them again.
Right. No, it's fine. It's no criticism. I was just curious how it works. But that's good like that. I mean, it's the simplest. I mean, it's just the essentials, basically.
Yeah,
everything else would just be like convenience stuff.
Yes, yes. And there's more stuff that we're going to go over, like more little things that we're going to go over. That's why at some point when I made a transaction, you could see that I was consuming a script that needed 17 ADA to be consumed. And that one, I think it was the one that could allows you to do more like a partial update. But
right.
It was maybe too complex for the lesson. So I just
sure. Cool.
Yes, and well, now that we are at it, like on top of that limitation, there's the limitation that the stablecoin developer doesn't get paid at any point in time. So I mean, with these contracts, at least the stablecoin developer doesn't get paid. So you could add like some sort of small fee at every transaction or something like that. And the last thing that I wanted to remark, we already like talking about it, so that's good. But one last thing that I wanted to remark is that it's a bit harsh. It's a bit harsh that in this exact transaction, it's a bit harsh that I'm taking the whole over collateralization of the currency. So if the user one, if the value dropped, so the user one doesn't have over 150, but has 147%. With this current smart contract, I can liquidate his position and get the whole 47% extra. But in the real world, that's too much of a risk. So you should have to like limitate the maximum amount of one of the solutions will be to limitate the maximum amount of collateral you can keep from the other person into like 5% or 10% at most, or 1% depending on the the risk factor, etc. But if you limit to 5% in the person inside 147, you can like liquidate his position, but at least the other person gets 42 back, and you get just only 5. But it's still worth it to liquidate someone else's position, so the incentive is still there. But the risk to mint the stable coins from the get-go is smaller. It's easier to get into the game if you at most lose 5%. So that's another improvement you could do on top of this, on top of what we have in this lesson. I think that was actually homework, in one of the homeworks in the Bluetooth Pioneer program. But yeah, so for now it works like this. Maybe that helps to understand the rest of the mechanism. So in this case, I get users 1 collateral by burning my just 10 of my USD Kenya. I still have 50. So if I wait for a bit, user 2 should have 40, but 15 more test ADA in the wallet. Takes a bit. Let's see if we can find it here. Not yet. User 1. Slow today.
I forgot, does preview also have 20 seconds slot on average time between blocks, or is it faster? Supposed to be faster?
I think it's
Things
supposed
also.
faster. Yeah.
Oh,
So I'm not sure why it's taking so long.
oh well.
Yeah, I mean, it's still like this is super long compared to. I never had to wait so long, so maybe it's something wrong. Let's see. Console. Let's see. Transaction submitted. No, it's good. All good. There you go. 10 seconds ago. So let's see this first because it's super. We have still 50. So it's going to update eventually. The interesting part is that as you can see, this is the inputs of the transaction. We consume 50 USDKs, USD Kenya, and we created 40 at the same wallet. So eventually we should get the 40. There you go. You should get the 40 back. But we also consume this script with the 15 ADA, and now it's part of our ADA outputs already. Now it's 155 and here's 157 almost. So we got users 1 collateral in exchange of 10 of our stablecoins. So that's the whole round trip. Let's see what happens when you spend all your stablecoins. Good question. Great question. So that's one of the bootstrapping problems of this algorithm. It assumes a lot of people have the stablecoins. So if you top up, and then if you top up if you mint some stablecoins and then like spend it on something else, the price of ADA drops. You have no stablecoins to actually redeem your own, liquidate your own position to avoid loss. So the algorithm in this case assumes more people has the stablecoins, other people have the stablecoins, so you can just purchase in an exchange the stablecoins and liquidate your own position. So that will be how you solve that. I mean, you have to, that's a bootstrapping problem because no one is going to be, if only one person mints and that person has no incentive to use that stablecoin, because as soon as it uses, the price drops. It has no way to buy its portion back to liquidate its own. But if everyone has these stablecoins and it's used like every other stablecoin, you can just use it in buy some in an exchange and liquidate your own position, and you still are not losing any money because you are just exchanging $10 for $10, liquidate your own position. You're the only one that can liquidate your own position if you're over the threshold. So everything is still good.
Another question, I mean, I was wondering, I mean, if user 1 in your example, instead of 10 had minted 1,000, for example, I mean, if there's not enough, I mean, if basically the majority is under collateralized, then there's not enough. I mean, can others, no, they can mint new ones then to liquidate him, right? That's the point.
Yes.
So yeah, right.
Yeah.
I mean, if I don't have any and you just, I mean, even the 10 now, but user 2 already had 50. But if he didn't, then he could just mint new ones with the proper collateral and liquidate you. So that's no problem.
Yes, exactly. Anyone can mint at any point in time. And
right.
actually, like when you create the collateral, it's an inline datum, so you can easily find under collateralized outputs to mint to liquidate.
And is that is this JEP project, right? That uses something like that. Is that the same algorithm? I mean, where did you get the algorithm? Did you make that up yourself? Is it like an existing one, or did you simplify an existing one?
It's based on the DAI Maker DAO. But this is a simplified version of.
Right. It's very clever. It's very cool, I think.
Yeah,
but the problem, of course, is if the price of ADA drops too quickly, right? If it, exactly. I mean, it only works if it's between 150 and 100% basically for long enough for people to liquidate positions.
Exactly. That's why some over collateralized at 800%. So there's like a bigger margin of time between you are between like 800 and 100. So you have more time for other people to liquidate that person's position.
Right. So this is secure, provided people, I mean, if they act, I mean, they have an incentive to liquidate because they can make money, and I mean, as long as the price of ADA doesn't drop too quickly, too low, this is secure basically and stable.
Exactly. Exactly. As long as the price doesn't fall below 100%, at that point, you're screwed, basically, because no one has any incentive to either mint more to liquidate others' positions because they lose money as in the whole transaction. So that's why you have to have huge, like real world is 600, something like that.
Right, but if the price drops slowly, I mean, even if then it's fine. I mean, if ADA goes down to 10 cent, it would still be fine if it's slow enough.
Exactly.
That in the mean, right. Okay, cool. Thanks.
Anyone else has questions or comments? Okay, so we have half an hour only. Oof.
Yes. But you don't have to explain everything. I mean, maybe, I don't know, show the off-chain, the TypeScript just briefly, and I don't know, just see how far you get. But I think it's more important. I mean, we have seen all the elements we have seen last lecture. I mean, with NFTs and so on. So I don't know. I think it's more important to understand the mechanism, which is very clever. I think it's really cool.
Amazing. Yeah. So, okay. Yes, let's do it quickly. So, one thing that Lars didn't have enough time to explain yesterday, was NFTs, which is just a minting policy that has to make sure that a specific a specific UTXO is being consumed, and that's provided as parameter. So the actual policy is parameterized based on a specific UTXO that is being consumed by that policy. So there's no way to mint two NFTs by using a policy like this one. And so in that case, you check that the policy consumes the UTXO that is being parameterized on, and that the amount of UTX of NFT of tokens minted is equal to 1. That's it. Then the oracle. This is a helper function to parse the datum. We're going to skip that. So the oracle has two parameters: the NFT and the operator, the PubKey hash of the operator. And you have two different options for the oracle. You can either update or delete the oracle. To use the oracle, you reference it, so there's no need to add the logic regarding that. The rate is just an integer.
Sorry, I'm very sorry. I just wanted to say oracle in this. I mean, if you did that for real, then the oracle operator would have a lot of power, right?
Yeah.
I mean, for example, if he deletes the oracle, then everything is screwed and nothing works anymore. If you delete the, and he could also, I mean, if he now, even though the price of ADA, I mean, if he gives a wrong price, I mean, he could now drop, I mean, from 100 cent to 70 cents or whatever, and then liquidate all the positions of people, even though that doesn't reflect reality.
Exactly.
So the real system, I mean, you would really need to trust the oracle provider or come up with like a more secure oracle somehow.
Yeah, I mean, I think I believe the only solution is like a proper decentralized oracle provider,
right?
Which is like an open issue to resolve in the whole blockchain world. But yes, in this case, I mean, I found a way to protect the user from the owner deleting, because in that case you can still burn your own stablecoins, but there's no way to protect it from changing to the wrong rate and liquidating everywhere else in this example.
But I mean, there are algorithmic stablecoins online on Cardano, right? Do you happen to know what oracles they use or how they do that?
Depends on the stablecoin, but for example, some of them own the oracle, but they charge on their own stablecoin, so they are incentivized to not break the trust with the users. But I think other than that, I'm not sure if there's like a proper mechanism. I think that's like, if you can solve this, you become a millionaire instantly.
Right. Sorry for interrupting. I was just curious about that. So I mean, one shouldn't use your code or if you do, then the oracle would be like a big, like weak point. I mean, people would need to trust the oracle somehow.
Exactly.
Right.
And yeah, you shouldn't in general. But maybe, I mean, maybe your validator can use like 7 different oracles that are not in control of the user, and to like take the mean or
Yeah, the
something like
median
the median
or something.
will be great. Yeah, better.
Right.
So that would make more sense. But in that case, like the oracle gets increasingly complicated for the lesson.
Of course, not for the lesson. I just want to point out that this is like unrealistic, or at least depends. I mean, except if you get a super trustworthy party to operate the oracle. Or yeah, sorry.
Yeah.
Yes.
Yeah, I think like realistically nowadays, taking the mean of 5 different oracles wouldn't be that bad. I think if it's owned by 5 different entities, that will be fine, I think.
Right.
I don't believe we have a better choice, actually.
Yes. Thank you.
Yes, no problem. So yeah, we have the parameters of the oracle that are the NFT asset class and the operator's public hash. So as soon as you deploy the oracle, this oracle can only use this NFT, and only this operator, the specific the operator that deployed the oracle, can manage it. So we have the parameters, we pass the rate as datum, and the oracle's redeemer, that the redeemer is just the 2 possible actions you can take, update or delete. So in the case the redeemer is, as you can see, as you can see, we are ignoring the rate because we don't really care about the rate, about the actual value of the rate. We only care that the rate is a valid integer. But other than that, it's just, I mean, for the update and delete, in our case, it's irrelevant. We only care about other stuff. For example, in the case that we delete, we just care that the person that deletes it is the operator. That's it. So the operator can delete independent of anything else. In the case that we update, we have to check that the NFT is an input of the transaction. So we are consuming the previous oracle. We have to check that we are putting the NFT in the output, that we are generating the output in the oracle's address with the NFT. So we are passing through the NFT, we are threading the NFT. We have to check that the operator is the one performing the action, and we have to check that the output datum is valid, because this datum is going to be read by our minting policy and our collateral to make decisions. So we have to make sure that it's properly formatted. And we have to go a bit fast. But I mean, we can, I don't know. I already recorded some lessons related to this, that this is a more up-to-date version, but you can still watch the other ones if you want. So check the operator signature, same as always, transaction is signed by, and we extract from the operator. We find if the oracle is the previous oracle UTXO is an oracle is being consumed by the transaction. We check that that input that we are consuming has the token. Then we check the same for the output. And then finally, this is different than things before. We check that the structure, the structure, the value of the datum has the correct shape. So we take our own output, extract and parse the oracle's datum, and this oracle's datum takes the datum, and if there's no output, returns nothing. If there is a datum, it parses it using from within data. And if there is a hash, we trying to find it and then parse it. So why this is important? Because here we are indicating that we want to return an integer. So this is if at some point we put a string or something else instead of a valid integer, this is going to fail and this is going to fail. So the whole transaction is going to fail. So that's how we check that we put a value, a proper integer as an output and not like a string and then it breaks everything else. So that's how the oracle works. Super overall. I mean, if you understood the intent on this, the actual implementation is just like searching here, searching here in the Bluetooth in the Bluetooth Haddock for the actual functions that you need to perform them, and that's it. So let's see, mint. So this is the front. In the front end, we have this mint oracles NFT button, and what this does is let's see, get final mint NFT. No, let's see, mint. Let's go down a bit.
So that uses Lucid, right?
Yes. Here's the entry point. Here we're using Lucid, which is a library that allows you to write off-chain code in the front end. And as you can see, we can use Maestro and other backends. So you don't have to run your own node. You can just use someone else's infrastructure. And it provides a bunch of functions to interact with wallets, to make payments, to mint assets, to test, to interact with, where is it? To interact with smart contracts here. So it's all written here, but we are going to show it in practice. We check that we have an address. This address is there because I'm connected with Nami in this case, but it can be Lucid or others. Then we use Lucid to get the UTXOs at this address. Remember that we need to consume a specific UTXO that we parameterize in the NFT with. So we run this get UTXOs that takes all the UTXOs. It just takes the first. We don't care really which UTXO we're consuming as long as we are consuming it. Then we get the final policy, the final NFT policy. In this case, we provide the UTXO that we want to consume because we just said that the NFT is parameterized based on the transaction output reference of a specific UTXO that we are consuming. So we have to provide that UTXO and like actually apply it to the script to get the final script. For that, Lucid provides this really nifty apply params to script function, where you can provide the script without the parameters applied. This script, you get it. This is for all contracts the same. This script, you get it by running this same NFT code. And after that, you get this value, this one, that you just copy and paste here. And there you go. You have your smart contract in the front end. And we apply this UTXO transaction hash and the output index and the token name to the NFT policy. Why we apply this? This is too fast. Because here the NFT policy requires the TXL ref and the token name. Sorry. So we apply the parameters in the front end without compiling or anything. We apply the parameters and we go back here to we use applying the parameters. We get the final NFT policy and the final asset class value. And now we perform the transaction. We create a transaction using Lucid. We create a new transaction that has to mint asset. Which asset? It has to mint this asset, that is the NFT asset class. And one of them, if we try to put two here, it's going to fail because it won't allow, the minting policy won't allow you to even, I mean, the important part is the on-chain. The off-chain has to adapt to the on-chain. And we provide a void redeemer. We don't care about it. And then we attach the minting policy. We need to have the minting to be able to run it. So we have to attach the minting policy. And we have to make sure that we collect the UTXO we are consuming. The NFT policy wants us to consume. So in this case, because we already chose this UTXO and we used it to parameterize the NFT, we can pass it to the collect from function to make sure that the transaction is consuming that specific UTXO. That way we can assure that this transaction will validate. We complete, this is like a wrap-up function, and sign and submit. This is basically it for the NFT. Then the Oracle, we have the two options to update and to delete. This is the on-chain code. And so in the off-chain, we have to build a transaction that does just that. And so we create the Oracle Redeemer that can be either update or delete. And if we go helper functions, let's skip the helper functions. All this is just so the UI works nicely, basically. Here, deploy the Oracle. To deploy the Oracle, we have to make sure that we have Lucid and an address. Then we get the pubkey hash. Remember, the Oracle asks for the parameters, and the parameters are the NFT and the pubkey hash of the operator. So we need that pubkey hash. So we get the pubkey hash of the current address. That's why we have to change it in the UI. Use that pubkey hash to get the final script. We do the same as before. To get the final script, we just make sure that we have all the values and then compile it, copy and paste here, and provide all the parameters that we need to provide and apply the parameters. And so once we have that final script, we we check that if we have minted the NFT first, of course, because if we don't have NFT, this is not going to work. And then we take, once we have the final script of the Oracle, we can calculate its address. We have this validator to address, a really handy function to take, you give it a validator and it gives you the validator's address. It's inside Lucid utils. Some login, setting the state. This is just to save everything and update the UI. I'm explaining the off-chain part, the Next.js part. That's it depends if you're going to use that or a different thing, so we can avoid explaining that. So Lucid, again, let's create a new transaction. This time, we are creating a UTXO at the Oracle address. So we have to pay to a contract to create an UTXO in that address. Which address? The Oracle address that we just created. What are we going to pay into that? We're going to pay the NFT asset class, the NFT we're going to send. And we're going to provide an inline datum of the rate. This rate comes from the front end, just to take it from the front end. And this rate is of type integer. So we create this UTXO that contains this as a value and the rate as an inline datum. We add a designer's key. We need to add the designer's key because else the Oracle, the validator has no way to know if the actual owner is the one submitting the transaction. Complete, sign and submit. We have our Oracle deployed. Then to update it, check all these checks that we have the Oracle deployed it and the address and whatever. This is all just checks to avoid having nasty errors in the front end. Get the proof key hash of the address, the owner of the Oracle, and create a new transaction. We're going to create a new transaction. In this case, we are updating. So there's already an Oracle. So we have to collect from that Oracle the previous value, the one that contains the, here I'm providing the Oracle with NFT UTXO, that this is the exact UTXO that contains the NFT. I'm using a background function to use that because you can see it in the off-chain code. But in this case, because we are collecting from, we have to provide the redeemer, and the redeemer is the update redeemer. The same update redeemer, because we are saying that we are using the update redeemer, this one. That means the validator is going to do all these checks. So we have to make sure that we are satisfying all these checks. And so updates, we collect from the previous one and we pay to the contract to the same Oracle address that we pay when we deploy it. And so we are passing along the NFT like we said, and we are providing the new rate from the front end. So this part is the same as when we deploy, because it's the same. We just have to make sure that we collect from the previous one to satisfy the validator. We attach the spending validator, the Oracle script. We have to attach it now because we have to run it to make sure we can unlock the value in the previous UTXO. We add the signers, same as before, complete, that's it. And this is if something's wrong. And to delete the Oracle, collect from, pay to the address, the owners of the Oracle gets the NFT, attach the spending validator, the owner signs, that's it. Let's go to the collateral or minting. Just in case we don't have time to cover everything, let's do the fun part. So here we have, let's move this there. Here we have the minting policy. Why is this here? I don't know. No, this is the. No, sorry. This is the all from the 26th.
Yeah, you are in the other one.
It's easier to do minting and stablecoin. Okay, this is the minting policy of the stablecoin. Our parameters. This is really important. The Oracle validator, this hash, the script hash of the Oracle validator is a parameter on the minting, on the mint script. The collateral validator script hash also, and the collateral min percent as well. So all this is part of the parameters that are applied to the script. That means our final stablecoin is going to depend the value, the actual value, the policy ID, and the asset class of the stablecoin. It's going to be dependent on all these two script hashes and the min percent. That means that there's no way, it's impossible to change these values. You change it, and as soon as you change it, you are not working with the same stablecoin. You have a new one that no one cares about. So this is important. Make sure that no one changes it. This is the this collateral min percent is the 150 over collateralized thing that I explained about. We have three options for the minting. We can either mint, burn, or liquidate. The minting, to mint, we only care about these three checks. In the case of burn and liquidate, because we work in tandem with the collateral validator, it's not just these three checks or these three checks, but also the checks of the other oracle. But in the case of minting, because we are not unlocking anything in the oracle, we just have to make sure that the minting amount is positive, has to be positive, that the minting amount doesn't exceed the maximum based on the collateral and the rate of the USD ADA, and that we provide a valid datum at the collateral output. We're checking another script output, not the minting. So I think all this is super interesting, but we might need to just go to this one, which is like the core. So we have to check the max minted amount. This max mint amount depends on the collateral outputs amount. We have a function to go to the outputs of the collateral and check and get the value logged there, and that we are going to log there, and check that that value is enough for the minted needed. So we let's go. That's it. So we have the collateral output. We have the collateral output here, and we take the value of that collateral output, and we provide that value to the max mint function that's going to give me an integer. That integer, the amount of maximum amount of stable coins I can mint, has to be bigger or equal than the actual minting amount that I am trying to mint in this specific transaction. The minted amount comes, you can extract it from this txin info mint, from the info value that we always use. You can extract the amount of tokens you want to mint and take the assets class value to just filter the one that you care about. So if the maximum mint is bigger or equal than the actual mint, we are allowing the user to mint. And how do we calculate the max mint? I wrote a short explanation of how it works, but this is just math, so it's not Pluto specific, so I'm guessing you can figure out. by yourself, but it's just simplification of a formula, and just multiplying the rate for the value, and that's it. So the actual calculation to go from the value locked to the maximum amount of minted stablecoins is this one. It's a super simple function. So once we have this, and let's go back here, we check that the minted amount is positive, and that the output has the correct shape. That means we are creating an output in the collateral validator. That means that collateral validator has to have all the values we say that it has, and with the correct shape. So we have to make sure that the minting policy is the same as the one that we have in our currency sim, that we have in our context, our own current, the one in this validator, that the stablecoin amount that we are saying we are minting in the datum has to be the same that we are actually minting, and the transaction is signed by the person that we are saying is the collateral owner. So this is another check you are doing. And then give me 10 more minutes. Then we have the options to burn and liquidate. And as you can see, we are repeating quite a lot. We have to make sure that the burn is negative. We have to be burning, not minting. We have to make sure that the burn is matched, the amount of stablecoins we are burning matches the same as they were minting in the previous, when we locked the collateral. Those are the same for both the minting, the burn, and the liquidate. But then in the burn case, we only need to check that the owner is the one that is actually trying to burn. So I mean, we don't really care about the current value or anything. We just want to make sure that the owner is the only one available to burn. But in the liquidate case, we want to check if we don't check who's the owner. We don't care who's the owner anymore. We only care if that collateral is below our threshold. For that, we use the check liquidation function that uses the max mint, the same max mint we are using before, but in this case, we are running this transaction in a different point in time. So this max mint that depends on the value of the oracle will likely change from one point in time to the other. So it's going to return a different result than in the minting case. So that maximum mint has to be smaller than the minted amount. The minted amount is negative because we are burning. So we have to negate it to get a positive amount. So this is how we check if some person can liquidate someone else's or its own position. Just we only care about the relative value between the collateral and the stablecoin. And as I said before, these two cases don't work alone, like the minting case, work with the collateral. In the case of the collateral, we hard-coded the token name, USD Kenya. We use the same parsing mechanism. So this is super simple, this collateral. Luckily, we can either redeem or liquidate. When we burn minting, when we use the minting policy with the burn redeemer, we in tandem use the collateral validator with the redeem redeemer. So we have to satisfy not only the mintings burn checks, but also the collateral validators redeems checks. And those are that the owner is signing. We check this twice for a reason, because so you are not you cannot consume it without running stablecoin. And this one, burning stablecoin amount mismatch, this one checks that you are burning the amount of stablecoins they are locked. And we have to make sure in both cases, in both the minting policy and in the collateral validator, that you are signing. This is not this is on purpose. In both cases, we are checking for the same, to make sure that you cannot use one without the other in a specific case that we don't have time to go over. In the liquidate case, we just care about the stablecoin amount, because anyone can liquidate. So we just check that the stablecoin amount that we are burning in the transaction is the same that inside the collateral datum. So that's pretty much all the checks we have to do. We can go over a bit of the off-chain code. We have the stablecoin file here. This is the off-chain code. Helper functions, we don't care about them. Let's go down. Mint stablecoins. To mint stablecoins, get all the values we need. We get the validator's address. Remember, we have to apply all the parameters. The transaction, this is something new that I wanted to explain further, but maybe other day. We use the read from function to both read from reference input and reference scripts. By using this read from, we are creating the transaction that indicates that we are just taking a look at the inputs and running the script, the reference script, but not actually consuming the UTXO. And when we mint, we pay to the contract, we pay the collateral datum of type collateral datum. This is just a mirror type. As you can see, it's a mirror type that the one we have in the on-chain. And we lock the value of, as you can see here, when I lock value, I write the value in ADA. So I just multiply that to get the value of Lovelace. And that's what we pay to the contract. The specific datum with the values and shape that we need, and the actual, as an inline datum, remember, this has to be an inline datum to be able to discover UTXOs that have not enough collateral. And this is the value that we locked. And in the same transaction, we mint the assets. We run the minting policy with the mint function, with the mint redeemer, and get the amount that we selected in the front end with the asset class that we got after applying all the parameters. And after that, we got, and that's the simplest one of the minting to burn. We have burn and liquidate are so much the same logic, needs pretty much the same logic and values. So I just put both in the same time and added some way to differentiate between one or the other. But in this case, we get the public hash, we get the redeemer. In this case, when we select burn or liquidate in the front end, this is when we choose if we are redeeming or liquidating. And this is how in the case that we are redeeming, as I said before, in the case that the collateral redeemer is redeemed, that means that we are burning for the mint redeemer, and liquidate, it means that we are liquidate. Then we create the actual transaction. Now, this is cool. We read from three different. We need the oracle now. That's the main difference. We need the oracle to calculate the liquidations and stuff like that. We need the collateral reference script to unlock the value locked in the collateral, because we are burning or liquidating in this case. And we need the minting policy to burn the actual tokens, the actual stablecoin. So we have to read from that. We have to collect from our collateral redeemer, and we have to mint negative amount of assets. That's how you burn. You mint in negative, and so in all that has to happen in the same transaction. You have to collect from the collateral redeemer and mint and burn negatively mint assets using the mint redeemer of your choice. We add the signers. In this case, yes, it works. Maybe it's not needed for if you're liquidating, but it is if you're burning. And this is inconsequential. This doesn't matter. You can just use the same as before. And that's it. This is UI stuff. Let's see, something else I wanted to say. No, that's good. Yeah, it was, I mean, and of course we have tests. So 28 stablecoin, Babal, test, stablecoin, unit test. I think that's what it is. So if, and we test if the mint NFT works. If we can mint the same NFT twice, that should fail. If deploying the oracle works, if updating the oracle works, if we have a bad signer updating the oracle, someone else tries to update the oracle, should fail. If the user can mint stablecoins, we have an end-to-end transaction, what we did in the front end, but automated. And we have all the liquidation cases. If we can, if we cannot, all those have to pass. So, any question? I'm guessing like a ton. Yes, sorry, Anderson. This is actually like 2 lessons in one. That's why we have
a question.
Yes, how is data 2 related to building data? Yes, so this is an important thing that the off-chain framework you use has to provide. So like every developer has to deal with this serialization of the values and stuff like that. So that has to be handled by the framework. So this, we have the rate. Let's see. This takes a rate. We assume that is in Pluto's data, but we need it. Oh God. There you go. We need it in Cibor to like encode it or to apply it. We need it either to encode it as a datum or to apply it to a script. But this is like, if you are building a tool like Atlas or Lucid for Cardano, you should be really worried about this. if you're using one of those tools, you should assume that comes within the package, right? Because that's the one thing that you always have to do, serialize stuff, that always everyone has to do the same. So if you're the developers of a product or an application and an app, you should use a framework that already gives you all the serialization functions ready to go, like Atlas or Lucid. But this is serialization because we are managing like the integers, Bluetooth data, CBOR. We're managing all those types at the same time, and there has to be some way to move from one to the other. Other questions? Awesome. You're welcome, Jason. Yes. Okay. I know it was a lot for the last lecture of the course, but I mean, you have available videos of this is the updated lesson. This is the updated code, so we're going to publish this. But not so long ago, I created the original code for this lecture for the Bluetooth Pioneer program, the 9th week of it, and it's mostly the same. So if you need to like rewatch this or the other one that I take more time to go over like each step, you can watch those videos or just like go over the documentation of each tool we are using and play around a bit around with the code. I think if you dedicate like one afternoon to this, you will get everything, and you will start to see like all the pros and cons of using one tool or the other, or doing things one way or the other. We didn't get into discussing why of a bunch of checks, because for example, what happens if I send a datum why do I have to check that the amount of minting is positive if I'm already checking, in this case, why I have to check that the mint is positive if I'm already checking that the minted amounts exceeds the maximum? For example, if I only care about the maximum amount, why do I have to also check that it's positive or whatever? There are ways that if you send a UTX datum to the collateral address with a negative value of minting of the minted stablecoins, you could actually use the mint redeemer to create money from out of nowhere, to mint from without locking your collateral. So all these nitty-gritties we didn't have time to go through, but this is actually one of the reasons that we have to check if the minted is positive and if the burning is negative. But yeah, I mean, that's taken into account, so that this is resistant to that exploit. That's another thing that you could try to test in your testings, in the test suite. Okay, so we have 20 minutes extra. So this was the last lesson. From now on, we have one more week for you to work on your own projects. And we are going to give you guidance, advice, technical and design, and whatever we can provide. We're going to do our best. So if you're working in your own projects, or you want to start working in your own projects or anything, we will have our full attention for another week. So I'm make a good use of it, of that resource. And I think that will be it for today. I'm not sure if Karina or Lars wants to add something else to it. Okay.
No, I think
No?
not. But
No.
it was a very nice walkthrough to a fully fledged D app, basically. Nice example.
Yes, I'm really happy about the example. I would like to, maybe next time we have to do our own lesson about this or something, some other app equivalent to go over the details. But yes, I mean, this is like a fully fledged app. Basically, you can just like do
Yes.
anything with this. I mean, that's it. That's an app. I mean, there's nothing more. I mean, if you, the only thing that you could like add is to use to create a backend with Atlas to update the Oracle automatically instead of doing it by hand or using some other way of getting the rate. Other than that, everything else works perfectly as it should. Okay, so see you Tuesday, same time.
Monday, right?
Monday. Yeah.
Sorry. See you Monday. And yeah, have a great week and make sure to ask questions in the Discord. Okay.
Right.
Bye everyone.
Thank you,
Bye.
everyone.
Thank
Bye.
you.